We'll kick off our afternoon session. First panel will be moderated by Joshua Johnson with PHMSA. I'd like to remind you too, to our webcast viewers, of which we have we had 440 at our highest count in the morning session. Thank you very much. If you have questions, there's a way to do that through your web browser there, so please do so, and we'll entertain those at the Q&A session. Then also, for those of you here, we have, as you've seen, the microphones, but we also have cards too if you'd rather write the question down on a card. But without further ado, I'll turn it over to Joshua. Thanks.
Thank you, Alan, and welcome back, and good afternoon. We have 3 more presentations for you this afternoon, starting with Thomas Boyker, who is the Director of Corporate Marketing for Pipelines in the Rosen Group, and I would welcome him up right now. Oh, as soon as I get your slides up.
Thank you. I want to talk about crack detection developments, and in particular here addressing EMAT ILI services. And we talked about the EMAT technology a couple of times already, so in this presentation I will more focus on the process which is required to make the EMAT technology to a real ILI service. These are the 4 topics I will address here. I will briefly give an update to the introduction again to the EMAT technology, and then focus more on the next 2 chapters here, what is required and what has been done to qualify and validate EMAT ILI technology. And then also, once the technology is qualified, how do you ensure that this is applied along the pipeline consistently with the quality required, and how can you actually also confirm and find out if the technology on this particular specific pipeline has worked well. And then the 4th one here is I will give you some short case studies with some data examples, so that you also see some nice colored pictures. So how is the EMAT technology working? We have a coil system with magnets. This is called the EMAT transducer, and the receiver looks similar. There is on an electromagnetic way, there is an ultrasonic wave coupled into the material. It's a shear wave, and since it's electromagnetic, there is no coupling, liquid coupling required between the device and the pipe wall. Now, if you have a coating on the pipe, some of the energy is then dissipating into the coating, so that is attenuating the signal. This needs to be taken into account later, but it can also be taken. An advantage can also be taken out of this, and a coating disbondment and coating types can be detected and characterized. So the way the EMAT is implemented, it's a high-resolution approach. So we have around the circumference a lot of sensitive areas, and on the right side here you see 2 examples of tools with the respective number of channels. From the transmitter side, transducer side, an ultrasonic wave is emitted and then received on the receiver side. If there is a crack anomaly in the way, there is a reflection generated, and you can see that on the numerical simulation on the top. Here on the left, the wave comes in, it's hitting the crack, part of it is reflected, and then the wave is going on. So the reflection and the transmission is recorded. This allows the normalization of the ultrasonic reflection as well as characterizing the coating. So basically there are 3 services which are available here with the EMAT technology, and that's crack detection, coating disbondment detection, and coating identification. Now if we look at the service itself, I found that interesting. In the morning here, there were a lot of discussions which actually can be found in this picture as well. So on the bottom you see, let's say, our service. We are providing here the ILI run, doing the data analysis, providing the reports. But there is a close interaction and communication with the customer required. The operator, the customer, has a pipeline integrity management program in place, and the service which is delivered by the email technology here needs to fit into this program. So there is an exchange of information, and as Brian mentioned here, we appreciate to get pipeline properties in advance, because this allows us also to determine what is the size of a critical defect, taking the tolerances of the tool and so on into account. And then going further, during the verification of the run, we have a close communication here with the operator, staying in touch with him, having people on site. So this was one project. If we now look on a longer term relationship with operators, with customers, doing subsequent projects, there are changes in the overall reception. Yeah? If we, for example, look at the mindset here, we go from a project oriented behavior to a process oriented behavior. If we look at what kind of investments, not necessarily monetary wise, are done in this cooperation, and in the beginning it's clearly here to build up knowledge and to establish communication, and then going further, operational excellence, improve first run success, better run behavior, and so on is clearly the goal. And on the bottom you can see here some elements which are addressed while going on. Now, if we now talk about qualification and validation of EMAT ILI technology, the question is, what has been done to demonstrate sensitivity, accuracy, and repeatability of the EMAT ILI inspection technology? So there are mainly three tools which we have. One is full-scale tests, pull tests on artificial anomalies. The other one is doing it with real anomalies, and then using field verification results. If you look at artificial anomalies, you can pretty much control the size and the shape of these anomalies. They are not representing real anomalies 100%, but you are controlling all the parameters. That means you can really sense out the capability of the system which you are testing, in this case the EMAT ILI system. If we then go for real anomalies, these are of course then features which you want to have because they are the same as you find them in the field, but there's often only a limited number of features. So but they are nevertheless very crucial to weight the results from the artificial anomalies. And then the field verification results are of course also very, very important, because here we have real anomalies and we have a higher number of anomalies due to the in the ditch work. We also have here in the work together with, for example, with RTD, we have seen that the automated phased array technology is really getting more and more acceptable. Just one remark here from the discussion we had earlier. The discussion was around whether verification in the ditch has the same accuracy like the ILI technology, and the question is, you should be a magnitude better to qualify, and to be a magnitude better, that is actually challenged at the moment, whether this is really the case. Here's an example of artificial defects. So you can see here EDM notches which were built into one of the test joints, and you can see here the signals. On the top right, you see a 10% deep feature, and you can see that the signal is start getting smaller. So with these kind of tests, you can identify the sensitivity of the technology. And on the bottom here, you see features brought into a long seam environment. One advantage, and if we talk about probability of detection, this can be a helpful tool. One advantage of EMAT is that the horizontal shear wave allows sizing across the entire wall. That means you get a depth size of a crack going from 0 to 100% theoretically. That allows us also to, if we talk about the POD, to focus on, to have a higher POD on critical defects than on, let's say, shallow defects. In this case here, this is the final data from a pull test with artificial defects, and you can see here reference defects which were known to us, and in addition qualification features which were in a kind of a blind test setup. This is now real defects, and here again it's the same principle. You can see on the shallow defects here the signal is going down. This type of testing is done to determine the sensitivity of the system. Field verification results are of course stored into a database. You see here the status as of today. It's not only that we have crack features in this in the database, but also crack-like features. This is also a very good input for determining the POI of the system. Coming now to the third topic here, and that is how do we ensure that the service is applied consistently along the entire pipeline, and how can we validate that the technology has performed on this pipeline as it should. In many cases, before we do an inspection, there is a request that we also qualify on specific pipe samples from the pipeline, from this particular pipeline. The reason for this is you can see you can see in advance if you can transfer information you already have into the system here to improve to work on the overall confidence of the system, or whether you have a specific case where you need to do other measures, look into certain engineering tasks, so that this specific task can be addressed. Another very important aspect is combined ILI technologies and operator data. For example, the circumferential MFL technology is doing a great job in improving the POI. CMFL is MFL technology, so there has to be some volumetric extent of the feature, and this allows to differentiate in combination with the EMAT from non-linear defects which are not crack-like, and so it's important to have a very high POI to have a efficient, effective process in place with regards to conducting the service. The operator data and also, let's say, our low priority data can be statistically analyzed and then put into the operator susceptibility models or integrity models. Field verification results, if there are dig-ups conducted, typically these are 360-degree verification. That means the entire joint is exposed to MPI, so that we really can see what is on the entire pipe. This is done to confirm thresholds. This is also done to confirm the POI, and also is used to adjust reporting conservatism where it was applied. Last but not least, and that is of course For the consistency, very important. This is the qualification of the personnel. The analysts are qualified according to AS&T. We, on the other hand, also we have a high automation of the analysis process, so that it's really a repeatable effort to do the evaluation. So this is just a simple flow here where you can see how the data are taken from the tool, and then the automated analysis is done, and then a manual review of those critical features which were selected is conducted. Here, this is an example. So the automated feature search is identifying identifying the. I can show it here. So the automated feature search generates a list of unclassified features. So the algorithm at this point does not know, is it a linear indication, is it a crack-like indication, is it mill-related, and so on. But the feature search is giving directly a length and a depth and a probability that this is a crack with each feature. Based on that, a manual prioritization of all anomalies is done with regards to a certain screening threshold. And you can see this here on the picture on the bottom left there. There is a dotted line which actually shows the screening threshold. So everything above will have the first priority to be analyzed by the analysts, whether it is a crack-like feature or whether it's another anomaly. And by doing this, we emphasize early in this evaluation process on the criticality of certain features. And for example, if you look at the blue ones here, which are mentioned that they have to be assessed, of course they are also assessed taking tool tolerances into account, so that they might also be flagged as critical features. And then the bunch of features which are below the screening thresholds, they are of course also further evaluated and reported, but with a different priority. This is an example from the field, 360-degree verification. The entire joint was exposed to MPI. Verification of all reported features were conducted, and search for false negatives were done, because that's one of the goals, to find methods to get evidence that no feature was missed in the pipeline. And by this, we get a verification of the POI. And as you can see here on the picture, 3 SCC colonies were reported with a certain depth and length, and below the reporting threshold, there were also other SCC colonies found, but none was above the reporting threshold. Similar process here. I mentioned the unclassified features. So the system goes in, 66,000 unclassified features. From these, 755 crack-like indications were reported, and in the first excavation campaign, 16 joints were excavated, 56 crack-like indications were found, positively verified, and again, no indication here was found which has been missed with regards to the reporting threshold. This is the last example here. This is from a repeated inspection, and here you see one particular feature picked up by the system in 2010 and then in 2013. So it's pretty obvious how good the data are repeatable. And this can, in this case here, why have I brought this up, is to show that if you compare the findings from 2013 with the findings from 2010, that it's actually a pretty narrow band, which also now is not necessarily also good for corrosion, for crack rose analysis, but also gives you another confirmation that you have done your work correctly, that the error band here is small enough. So conclusion, crack detection services require a transparent process to demonstrate the confidence in the service. This has been adapted to EMAT ILI service as well. Full-scale test, field verification, and historic data are the basis to increase confidence in performance validation. Based on qualified EMAT technology, continuous improvement is conducted to achieve operational excellence. Quality assurance process to ensure EMAT ILI service performance along the entire pipeline. That's not a complete sentence, but I leave it like it is. Okay, thank you for your attention.
Our second presenter this afternoon is going to be Jeff Foreman, who is a Senior ILI Technology Advisor for PII Pipeline Solutions.
Thank you, Joshua, and thank you for giving the opportunity to speak today. I'm not going to give a sales brochure type of presentation here. Hopefully, we're going to have something a little bit different and a bit faster. So first of all, we're talking a lot about technology today, and crack detection isn't about just technology, it's a process. And the thing that we must remember is that human beings make the decisions on what the tools see. So Brian Lee said, you know, we would love to have Mensa pigs, and we do have them training. But human beings make the call at the end of the day. And our experience over the years is that the tool sees everything. The human beings make mistakes. And one of the continuous improvements that we've come about over the years is making sure that we train those mistakes out of the analysis process, i.e. we put it in our training material and we blind test our analysts to make sure that they don't fall into the same trap again. A quick history lesson. This is not new. This has been around. Ian Calhoun talked about the Canadians having issues in the 80s, and I was around with British Gas in the 80s, and we were already worrying about STCs on a brand new system that we'd put into in the UK. So we came along with a crack tool called the Elastic Wave way back in 1982 and used it extensively in Canada and the US in crack detection. What we then realized was that, you know, people are asking us find two types of cracks, single cracks and crack fields, and just find them. We'll deal with the rest of it. And so we started doing that. And then we tried to get clever and make it into a sizing tool, and we realized that the sizing capability of that tool was limited. It was a threshold of 25% of the wall thickness, plus or minus 25%. So you either had a 75% crack or nothing, really. But that's what it was back there. And then the first CD tool came along, and it was better than ours, so we bought the company, as a man says, with a razor. And we bought Piptronics with the ultrasonic tool. And it's very, very good, very reliable, very repeatable. And then we came along, the gas operators got a bit upset because this really served the liquid market. And we needed something for gas, so the EMAT tool was designed back in 2002, the original generation. But it fell into the same problems the Elastic Wave had, and that was it couldn't discriminate between SCC colonies and laminations, or stable features, or whatever we're going to call them now. Basically, defects that you don't want to be digging up. So we came up with a generation 3. We put another sensor on the tool to discriminate the difference between laminations and corrosion and real cracks. And that's been very successful ever since. Then Harvey told us all about the science, so I don't want to go into how everything works because you've already been bored to death by all of that. So the USCD tool works as a shear wave, so we know how that works. It needs corner effects to size. The next generation, or the state of the art, as Harvey explained, because the stuff he was going on about is still research, but the state of the art right now is phased arrays. So the phased array tool came out, and we call it the Duo because it can do corrosion and cracking in one go. It came along. I can't see the screen here, but it came along in 2002. No, 2006, and then we upgraded the CD tool. We made it a higher resolution tool, a faster tool. It needs to work at 7 feet per second these days. So you're thinking about technology, you think about the new technology that Harvey was talking about. He was talking about walking a length of a pipe. Well, you try and walk a length of a pipe at 7 feet a second, because that's how fast the tool goes through and measures cracks. So since 2010, we played around with phased arrays, and we increased the circumferential resolution by a factor of 2. We also played around with multiple angles, and I'll explain a little bit about that later on. And to date, we've done about 40,000 miles of inspection. But in parallel to that, the analysis process has been updated. And that went from that terrible size and spec for elastic wave to buckets, which everybody hates, to absolute depth sizing with a tolerance, changing algorithms for SCC, because SCC is harder to depth estimate than single cracks because they have the shading effect on each other. And then we got to the 1 million reported crack marker. And what we're playing around with now is looking, as Achim mentioned in his talk, we're really looking at analysis and looking at attributes, looking at the learnings, features that have failed post-ILI. What did they look like? What have they got that's different? How can we analyze what the tool sees better? And when we first took over the CD tool, it was a year to get a report. And that's not really useful to people. And then we were asking people to dig so that we could calibrate the analysis algorithms to get the sizing right. And that doesn't help either. So what we've done as we build up our knowledge is to automate the whole processes. So now we're down to 2 to 3 months for a commercial report. So what can the tools do today? So we've already talked about shear wave, phased array, and Thomas mentioned EMATs. And all I'll say about EMAT, our EMAT tool is very different to Rosen's EMAT tool in that they're a short wave tool, we're a long wave tool. We have 6 sensor carriers, which means it's a very long tool. But the advantage of that is that it can actually see cracks and dents, and it doesn't get affected by the dent itself. And I'll come into that a little bit later. So we were asked to look for 2 types of cracks. Lo and behold, we talked this morning about different morphologies of cracks. We found 16 different types of cracks that we now have to identify and size with the modern day tool. And I did this little diagram. Please forgive me for the graphics. It's not fantastic, but we're trying to show what ERW and what a submerged arc welded defect would look like. And then I did a little table on capabilities. What can we see? We can see everything. What can we size? We can size most things. We are challenged in some areas, though. As Harvey explained in his presentation, shear waves rely on corner effects. Corner effects means that the crack has to be at the inner or the outer surface of the pipe. If you look at crack 6, for instance, it's a mid-wall crack. Now, we can detect it, but we can't size it very well. But EMAT can. And that's one of the advantages of EMAT. As Thomas explained, it's a complete wall wave. And then we come to DSAW welds and SAW welds, and lack of fusion, and hook cracks emanated from the shape. They're not actually aligned defects. So they're a challenge. We detect them, but sizing them, where is the hook? Where does it end? And Achim explained that that's an area that they're looking at as well. So the current capabilities of the tool are stated on the screen. And I just wanted to get one thing out. when people look at confidence levels for POD and POI, they're given for the minimum size defect that's on that page. That's 1 inch long and 40 thou deep, or 2 inches long and 80 thou deep in EMAT. The bigger the crack, the bigger the confidence. The whopping ones that are going to fill the pipe, you don't miss. And I just wanted to put that out there. So where we're going next? Well, if we look, we're always accused of hiding behind our specifications. ILI vendors, we're very good at that. It's not acceptable anymore. We're in this business for zero failures. We're partners with our customers for zero failures. So therefore, we must now look at means of finding those tail defects that challenge us, like where is the end of a hook crack? What happens if you've got a crack and corrosion, whether it be internal or external? Does the corrosion affect the size and capability of the CT tool? Well, what do we need? Well, we're always looking for money, and we're always looking for help. GE have spent $100 million on crack development. And believe it or not, the crack tools we have today, when we run them, is only 10% of our total fleet. So therefore, 90% of the time it's MFL, and only 10% of usage is crack detection. So I don't think people are voting with their dollars in this technology. It's not new. This is not new, and it works. Dig feedback, if we get more dig feedback, it's been tremendous getting feedback from the clients that we have got, because it gives you confidence to go to absolute depth sizing. It gives you the real proof with real defects from the pipe that you can actually put a tolerance on, and even a conservative tolerance on the size. And then to get those tail defects, what we need is a repository of real features. We want pipe with corrosion and cracks in it. We want pipes with dents in it and cracks in it. We want lack of fusion defects from saw welds. We want to be able to prove the algorithms and the different technologies that we need for sensing, and the different angles we might go to get a better look at these features. So that's what we're asking for. And with that, I thank you.
Our final speaker of this panel is going to be Ted Anderson from Quest Integrity Group.
Thank you. Well, I'm going to switch to...
Let's lift that up just a notch so it doesn't bounce on the... There we go.
Okay. Can you hear me still? Great. Well, I'm going to switch topics up a little bit and go from detecting cracks to analyzing and assessing cracks once you have the basic data. And I'm going to also try to play the role of a myth buster on some of the things that the industry is accustomed to using. So I'll warn you, some of you are probably not going to like what I'm going to say. So with that out of the way. Well, let me start with a myth that doesn't have anything to do with the pipeline industry, but by way of example. In this story, I have to credit the latest Freakonomics book. This story was in there, and it's out there anyway, elsewhere as well. But back in 1990 or earlier, if you'd asked your doctor what causes ulcers, he or she would have said, well, it's stress, and then you treat ulcers by taking acid blockers, and there's prescription drugs like Tagamet that were developed for that purpose. And that's what the medical knowledge was back then. Well, it turns out that was wrong, that ulcers are not caused by stress, but rather they're caused by a particular type of bacteria that if you happen to have that bacteria, in most people it will cause an ulcer. So in pipeline terms, they thought it was a corrosion problem, but instead it's third-party damage. And the treatment, rather than prescription drugs like Tagamet, is antibiotics. It will clear up an ulcer and it will actually be a cure, whereas the acid blockers might have made you feel better, but the ulcer was still there. And so oftentimes surgery was required. Well, this was discovered back in 1984 by a couple of Australian researchers, and one of them actually went to took the step of actually ingesting some of this bacteria to prove it. He ingested the bacteria, and 3 days later he had an ulcer. Now, you'd think that when they published their findings, they had fairly convincing evidence that the medical community would immediately say, okay, now we know that we were wrong. Well, it took over a decade, or around a decade. Now, physicians are generally intelligent people, well-educated, so why did it take so long? Well, doctors are also humans, and they learn a certain set of concepts in medical school. And when someone comes along and says that, well, something you learned in medical school is wrong, there's a lot of resistance. Plus, you have pharmaceuticals who spend billions on new drugs, and they spend who knows how much on developing Tagamet, and you're all of a sudden telling them that it's not effective for what it's supposed to treat. That there is some resistance. So I'm about to talk about some areas in the pipeline world which I think fall into that same category, and I'd ask you to keep an open mind, or barring that, if you throw anything, just make sure it's not something hard that does bodily harm. Okay, first I'll give you a quick, like 30-second refresher in fracture mechanics as applied to pipelines. If you have a pipe with a longitudinal crack in it, there's 3 regimes of failure depending on the toughness of the material. If you have very low toughness, you'll fail in the linear elastic regime, where you're still well below yield and there's no significant plastic deformation in the pipe. It's a very brittle failure. At the opposite extreme, you're in the plastic collapse regime, and Brian Lee's talked about that this morning. You have, in the plastic collapse regime, a crack behaves pretty much like metal loss, and it's governed by strength properties, and the burst pressure is independent of toughness. Then you have this in-between region, which is called elastic plastic fracture, and fracture mechanics will handle the first 2 regimes, and then once you get onto that plastic collapse limit, then you use something else. So with that in mind, my myth number 1 is the venerable log secant model. Now, I have the word modeling error there. Let me explain that. But first, I want to say that this original work was actually quite impressive back in 1970. Fracture mechanics was still in its infancy, and the Battelle project that was going on late 60s, early 70s was actually groundbreaking. And they actually started with they developed the metal loss equation first, and then they observed that if you had low toughness, the metal loss equation overpredicted burst pressure. So they adapted the metal loss equation to be a function of Sharpe energy, such as the Sharpe energy went to 0, your burst pressure would go to 0. But that equation did have a modeling error in it. It has to do with using the effective area relationship, which works great for plastic collapse, but it doesn't work in the fracture regime, as it turns out. But they wouldn't have known that back then, and it's a forgivable error, because that's what science and engineering is about. We try something, we develop a model, and it was for its time, it was a pretty good model, but then there's some shortcomings that came out of it, and it was, for one thing, it produces some unusual results for very shallow cracks. And so as a crack gets shallower and shallower, it starts predicting burst pressure results that make no physical sense. So then came the modified log secant model in 2008, and rather than fix the modeling error, what it did was it left the same modeling error in there, but then it applied an adjustment factor to get rid of the shallow flaw effect. Well, it's kind of like when you take a prescription drug, you've heard all the various commercials. They tell you what the benefits of the drug are, and then they spend the other half of the commercial telling you what all the side effects are. Well, in this case, you had keep carrying on that analogy, the adjustment factor was treating a symptom, it wasn't treating the problem, and it had a side effect. This is a plot of burst pressure versus Sharpie energy, and it's normalized by the B31G equation. So at the above about 30 foot-pound Sharpie energy for this particular pipe configuration, you get essentially the same answer in burst pressure as you do from B31G. As you reduce toughness down to 0, the predicted burst pressure still is about 85% of what the metal loss equation gives you. So what happened was this adjustment factor removed the dependence on toughness. So you have an equation that's almost insensitive to toughness in predicting burst pressure. And in fact, that makes it superfluous because it gives you almost the same answer as B31G, so why do we need two equations to predict plastic collapse, which is all this is doing. It's not predicting correctly in either the linear elastic or the elastic plastic regimes. So if you look at what this means in reality, it produces unconservative results. The blue curve is my representation of reality of what we expect burst pressure versus toughness to look like. And the yellow curve is modified log secant, and that red area represents unconservative predictions. A real-world example, this morning the Mayflower, Arkansas incident was mentioned. If you use a modified log secant on that particular incident, you predict that it didn't happen because it way over-predicts the failure pressure. Now, more recently, in some of the PHMSA-sponsored research, there's a new proposal that said, okay, yeah, we recognize it doesn't work at low toughness, so we'll introduce another model for linear elastic, and that's based on some work that was done at NASA in 1980, and it actually applies to a flat plate, not a pipe. But let's be generous for a moment and assume that it gets the linear elastic part correctly. You still have an uncertainty zone. They've reduced the size of the red zone, but haven't eliminated it entirely, because you have one equation for linear elastic, another equation for plastic collapse, but then the elastic plastic regime, which actually is where most pipelines live, is not predicted correctly, and it's unconservative. So what do you do about that? Well, there's the current state-of-the-art in fraction mechanics. Most codes and standards use something called the failure assessment diagram, which I won't go through in detail, but it does predict reasonably well what happens. You have the linear elastic, elastic plastic, and the plastic collapse embedded in this model. Now, who's using this approach? Well, if you look at oil and gas, the upstream oil production, especially offshore, is characterized by British Standard 7910. At the downstream side, in the refining world, they use API 579. And midstream pipelines, for girth weld flaws in new construction, API 1104 also has a failure assessment diagram method. So you can see the odd man out here is the pipeline industry with respect to longitudinal flaws. They're not using the failure assessment diagram as an official or widely used policy. Now, some people, including our company, uses API 579 for pipeline flaws, but generally speaking, this particular side of the pipeline industry is out of step with the rest of oil and gas. Now, there is, in addition to API 579, there's an alternative that's just coming off the assembly line, if you will, and that's some new PRCI research which we've completed, and we're currently finishing up the final report. And what that is a development of a new state-of-the-art crack assessment method, which actually leapfrogs the technology of what the rest of oil and gas is doing, and has the best available prediction model. And it's based on doing a couple hundred finite element runs of pipes with cracks, and then curve fitting them. And so the report should be up on, if you're a member of PRCI, it should be up on their website, the draft report, within a couple of weeks. Now, I have two more myths, I'll get to them fairly quickly. Myth number 2 relates to log secant, and that's the idea of leak rupture curves. And the concept is, if you plot burst pressure versus flaw length for different flaw depths, the through-wall curve intersects the other curves. So if you're above that red line, you predict rupture. If you're below the red line, since you have a very short, deep crack, the prediction is you'll have a rupture of the remaining ligament, but the through-wall crack will remain stable, and so all you have is a leak. The problem is that this doesn't actually happen when you look at a modern fracture mechanics model. Here's what API 579 predicts. These are burst pressure versus flaw length for different depths, and the bottom light blue curve is through wall. And notice that the through wall curve doesn't intersect the other ones. And I thought, well, is that just a problem with the math of the API 579 method? So I ran some finite element simulations. I compared an 80% crack to a through wall crack at various lengths, and I found that from the elastic plastic FEA, the through wall crack was always worse in terms of crack driving force than the 80% flaw. So that's myth number 2. And then the final one is what's now in the TTO5 document on rating severity of pressure cycling. So you not only have to predict failure, but you also have to predict fatigue crack growth due to pressure cycling. And TTO5 has 4 categories of rating pressure cycling: light, moderate, aggressive, and very aggressive. And this lists the assumed pressure cycles that are representative of those 4 different severity ratings. Well, there's a couple of issues that I have with this, one of which is the categories are subjective, which, okay, most rules-based approaches do have some degree of subjectivity in them, so that you can forgive it for that. But the more serious problem is that when you do a fatigue crack growth calculation, the rate at which that crack grows is a function of the absolute cyclic stress, not the stress relative to SMICE. Whereas this is all normalized by the yield strength, but the real world doesn't work that way. And so as I'll show you in a moment, the way it turns out is that you tend to be conservative for low strength materials and unconservative for high strength pipeline steels. An alternative that we've recently come up with is a cyclic index, which is a single number, which is the full definition of it is it's an equivalent number of cycles per year that are full MAOP, 72% SMICE, but tagged to X72, because as I said earlier, you can't normalize the hoop stress by the SMICE in fatigue calculations. You have to take the absolute hoop stress. So we just picked X52 as just a marker, yet we had to draw a line in the sand somewhere. And you can view this number as a pressure cycle speedometer. This graph shows monthly data over a 4-year period on a particular liquid line. You can see that index kind of bounces around a lot. In one case, it goes from 90 to 20 in a couple of months. And so we think it's a more effective way to quantify how aggressive your cycling is. Now, if I take these numbers and I run them through the calculation of this cyclic index, this is what the cyclic index predicts for the different categories. And you see that the cyclic index, which is based on absolute stress, varies significantly with the pipeline steel grade. So for example, you see the 2 circled numbers. Under X42 aggressive, you have a number of 53, and under X80 mild, you have a number of 59. So those numbers are pretty close. So what it's saying is if you can have the identical cycling in an X42 pipe and an X80 pipe, in one case you consider that cycling mild, and in the other case you consider it aggressive. And it's the same exact cycling, which will produce the same exact fatigue damage. So this is an alternative to that. And I believe that's my last slide, so thank you very much.
Thank you to our panelists. Do we have any questions for a member of this panel? Always so many post-lunch questions. Oh.
Dean with Kipner. So I have a question for Ted about that leak rupture differentiation. We follow your suggestion on the new PRCI project results. So how we define the difference between leak and rupture? Because all your curves are all above the through-wall thickness results.
Well, you'll,
the criteria to define rupture and leak.
yeah, is this on? Is this on? I'm not sure how to, oh, now it's on, okay. Well, you still will, I'm not saying that you'll never have a leak versus a rupture. What I'm saying is that you won't have a deep crack that all of a sudden suddenly breaks through to the surface and then stays stable. You'll still have fatigue cracks that grow through wall and will leak. And so the best way to determine when you're going to have leak versus rupture is to look at the critical through wall length. So if the critical through wall length is, say, 2.5 inches, then everything that's less than 2.5 inches will grow through to a leak, but everything that's greater than that will grow to an unstable rupture.
Okay. Then the second question is for the BSF 910 and API 579, the FAC curve is different based on the 2013 version. So which one, which to choose according to experience?
Whether to use BS 7910 or 579, is that's your question? They're both roughly equivalent. BS 7910 just came out with a new version. 579 is due to release a new version at the end of this year. It'll probably be January of next year. But they're both roughly equivalent. They're not identical, but I'm on the API 579 committee, but so I have a bias in favor of that. But technically, there's not really much difference between them.
Brian Lease, consultant, et cetera. The comment relates to the last question about leak versus rupture. Several years ago, a project was done in regard to critical flaw lengths for pipeline applications and validated with a number of experimental outcomes in the laboratory. And that's available certainly to PRCI members, published circa 2008, 2009.
Question in the middle.
Dave Katz Williams. Ooh, it's on that. Hey, Ted, thanks for helping Sergio and I over the years, with API 579. I think the only exception I'll take is, not that I like my refinery brethren, but while they're using API 579, we've been using it in the gas transmission and liquid transmission side. TransCanada, Williams, a number of companies have been using API 579. And I'd reference our paper at IPC jointly with GE on our first USCD run back in 2001. So in 2004, we all kind of jumped on that bandwagon, and I jumped on it mainly due to Dr. Gao and Dr. Krishnamurthy and my Canadian brethren that would share all their data with me back in the early 90s.
Yeah, I hope I didn't say that no one's using 579. I think I mentioned that some have been using it, but it's not yet widespread. There's still a lot of people using one or more incarnations of log secant. But I appreciate you guys being early adopters.
Question in the middle.
Just to back that up, then what Dave said, what would you suggest? Because I think people are using log secant because it's easy, and it's like with tools, right? You have an easy tool, and use it. That's why we're using Sharpie, and we're not using J, because in order to get J, you gotta pay 3 times as much, and you don't have enough pipes. In order to build a database, it's very difficult. It's very easy to get Sharpie everywhere. So that is okay for level 2. For level 3, we can't do it. Level 2 has a lot of conservatism. So how do we move on from the simpler tools, less accurate tools, to something like 579 on a wider spread basis, where we don't need a PhD to run this, right? Because some of these things are complicated, right? And assumptions, etc. So, any suggestion on that? And also widespread. I mean, not like we would have to come to you for service.
Yeah, well, we actually have another way of taking your money, though. We do have a commercial software package. It's fairly user-friendly, but in addition to, we haven't put it up on our website yet, but we have developed a simplified Visual Basic / Excel application that we're going to give away for free that does the basic API 579 failure assessment diagram. So that'll be eventually available from the Quest Integrity website. And if anybody's interested, I'd be happy to send you an advanced copy. It hasn't been fully vetted yet, but yeah, give me your business card and I'll send you a free copy of that one.
Yeah, remember, we can't see you, so waving your hands doesn't really help all that much. Any more questions? All right, with that, I would like to thank our panel again, and we're going to bring up Jim Merritt, who's going to introduce the next panel. Thank you very much. Thank you.
First up, I want to introduce Mark Piazzi. Mark has worked the last 9 years in industry-leading environmental integrity and research programs. Mark works now for Colonial Pipeline as the program manager for integrity programs. Prior to that, Mark worked quite a few years at PRCI in the integrity-related programs and technology development. Mark? I don't even see the mouse. Okay, there it is. Mouse.
Okay, while Jim's getting started, I'll say good afternoon. Thanks for the opportunity. Again, I'm representing PRCI and talking about the R&D programs, which I have a very close connection to, spending years there, and still work on a lot of the programs as a Colonial representative. We're going to have a little twist here on the presentation, though. It's going to be me starting out talking very broadly about the R&D programs that are addressing cracks and crack management, and then I'm going to turn it over to Jason Scow at C4 Technologies, who's going to talk about a specific project that was run that deals with ILI crack tool reliability. We've had a lot of great presentations, we've heard a lot of great information, great news on the performance of tools. I think Jason's presentation on that study is timely and will fit in well with what you've heard here all day. So I'm going to be very fast. If Jeff Foreman thought he went quick, he hasn't seen anything yet. So, topics to cover, big picture. The idea here for this panel was research and roadmaps. So, I'm going to talk about roadmaps in a general sense and give you some ideas of what's being worked on in PRCI. Talk about integration of the programs and how we're using programs to manage the crack issues, bringing those things together through a crack management task force, which I'll talk about soon. And then always going back to integrity management. All these R&D projects, all the work we do always has to come back to the integrity management programs that we rely on every day, all the aspects of the R&D that's done. Like I said, we'll go into the ILI crack tool reliability, a little deeper dive into some data, and then I'll come back and talk about the look ahead on R&D. So balancing factors for R&D programs. You know, a lot of us are research oriented. We do a lot of detailed work at our jobs on a day-to-day basis. And we get into these R&D projects and programs and really sometimes get mired down in the details, right? The details matter, devil's in the details, you have to pay attention to it. But we're also trying to make sure that, again, we stick with and understand how all this applies on a day-to-day basis to the integrity management programs that operators use every day. We do that through the roadmaps. We have developed, through PRCI's technical committees, developed a whole series of R&D roadmaps that deal with programs that deal with topic areas, focus areas that are relevant in the PRCI research programs, and use those roadmaps to really guide and drive the direction. There's a lot of different things going on. Again, you've heard some great presentations and great information. So we really need to use these roadmaps to effectively manage the work that's being done. So again, these are a simple model of the activities being done in the research community, but they're also primarily used as a communication tool. We've spent a lot of time developing those, and I think with the R&D forum over the next couple of days, the concept and idea of using these to communicate what the true industry needs are, what the drivers are, how we're going to address those through projects and programs, and really help confirm what the top R&D outcomes are, getting consensus across the industry on those needs and gaps, and driving projects to achieve the outcomes we need, and then looking at things like allocating funding. So they're really, really important to providing some structure around managing and maintaining these R&D programs. So at the bottom, we've got separate roadmaps for ILI, for NDE, for assessment, for materials, for fracture. Lots and lots of these have been developed, and again, we have to find some ways and methods to coordinate and communicate across the crack world that we're dealing with. So here's a slide of the an example of the R&D roadmaps. This is the format and content that we're using in PRCI, generally speaking, for most of the primary programs and focus areas, where you define your driver, and as you progressively work across from left to right on this spreadsheet-like form, you start to whittle down and get into more and more details, eventually getting to the point of defining what your project needs are, when they're going to be done, what resources you need. It's very, very hard to put all of this in one slide. Excel and PowerPoint don't really work very well together, and my skills at editing are limited. So I've attached just one piece here that shows the improvement for assessment methods. You just heard Ted Anderson talk about work at PRCI. There's also other projects that are being done to work on seam assessment methods, crack assessment methods. We may hear more about those at the R&D forum, but again, I've got 15 minutes between the two of us, so I can't really spend a lot, if any, time going into the details. This is, again, just to give you some idea and understanding of how these roadmaps are being used on a day-to-day basis. So I mentioned the Crack Management Task Force. So within PRCI, as you can see here, we have lots of work being done in the detection and characterization aspects of the projects and programs, and the assessment side, prevention side, repair side. Those letters and numbers you see are just PRCI speak. Those are project designations and nomenclature that we use internally, but it just goes to show the level of work that's being done in those different aspects of integrity management. The Crack Management Task Force is a group of PRCI member company representatives who are involved in each of these four elements and work at most of the technical committee meetings to ensure that we have coordination. We've got the assessment pieces being tied to the detection and characterization projects, which aren't necessarily always the same group of people working on these issues. So this is an effective method that we've applied to date to ensure that we've got the communication we need, that we're driving those R&D programs and getting the results. You can see detection and characterization, lots of work being done there, as well as on the assessment side. So the collective outcome of all this work, again, though, is going back to practical guidelines for operators to implement integrity management programs. So here's one we spent some time on, and this is my my segue into Jason's presentation on the ILI Crack Reliability Project. So there's a big emphasis right now in PRCI and looking at ILI technology. PRCI and DOT have a joint R&D program on evaluating the performance of ILI technologies and driving technology improvements. This is the roadmap that was developed for that program, and highlighted in red are several of the aspects that are going to be covered in the presentation that Jason's going to provide in just a few minutes. So again, this is a practical example of what we're doing in the research programs, how we're using these roadmaps to help guide and drive our direction, and then developing some significant outcomes that you'll hear from Jason right now. So I'm going to stop there and let Jim.
Thank you. We're very responsive today. I want to bring up Jason. He works for C4 Technologies, and he's spent 12 years experience in engineering design and management, and over the past 6 years his technical work has been in pipeline integrity management. So let me find Jason. Just leave the other one up. Yeah. go. I also want to say real quick before Jason starts, that at the registration desk was the handout of the DOT projects. There's 36 projects on here that we've worked on over the last, 10 years now. And it listed different projects, so, and some of them interface with PRCI.
Okay, thank you. Jim has graciously offered to blame me if we cut into the break, so I'm going to get started right away. I've got about 10 slides, and I've got about 10 minutes to get through them. I'm going to talk about the PRCI project NDE 4E, and here we're talking about ILI crack tool performance evaluation by comparing what was found in the field with what the tool called. This project had 3 objectives. I'm going to cover the first 2. The first one was to have an industry collaboration to collect data and validate it. This is data that represents real-world situations and a lot of varied field conditions that can be found. And we wanted to put that in a database for long-term storage and analysis. The second one was to evaluate the performance of the ILI tools based on this data. Here's a summary of the project. We collected roughly 51,000 crack features from 80 different ILI tools, tool runs from 8 different companies. ILI performance was assessed as a function of remaining strength. Okay, this was a choice that we made. It didn't have to be done this way. A couple of the reasons why, though, were that the pipe strength combines length and depth and is also relevant to the integrity management process. We could have done a similar thing where we were tracking performance with something to do with area, but what we found is that length or depth individually was not enough to characterize the ILI performance, so we used remaining strength. The second thing is that the rate of detection that we found increases with increasing feature size. I think this echoes some of the comments that were made previously. I've got a slide showing rate of detection performance that will be coming up in a couple of slides. Lastly, field measurement precision and accuracy is critical to the ILI performance evaluation. The way we mitigated this, of course, we're using field data. The way we mitigated this is we used feature profiles when possible. Feature profiles have a lot more information about the crack feature itself, and they provided a lot of insight as to where the tool is doing well and where it needs to be improved. Also, depths that were measured by grinding and measuring the remaining wall thickness were found to have a better correlation with the ILI data than some of the other techniques. And I think there are some similar comments to that made previously as well. Okay, so let's get started here. The data summary, I'm going to focus on the bottom row here. You can see there's 51,000 roughly features that were collected in total. There's a column there greater than 21 or greater than 25 by 1. This is often used as a specification for performance. And you can see that we have roughly 5,000 features that are greater than that. So we found a lot of small features, and the tools, in fact, were detecting a lot of these small features. In the last column there, you can see the profile data. We had only 400 of these, but these were extremely insightful, and as this project goes forward, we're going to be looking for more of this type of data that provides a lot more detail. I've just got one slide on the data management process. This was extremely important when bringing data from various companies together. We had to go through a data validation process, come up with a nomenclature to make sure everybody was talking about the same thing. The data validation process had 35 different validation rules in it, and if the data didn't pass the validation, we would look for the outliers and try to figure out what was going on there. The outliers can be the most important data points sometimes, but if they turn out to be errors, they can draw the wrong conclusions from the data set. So we wanted to be sure that when we were looking at outliers that they were telling us the proper story. So we went back to the original field notes. We sometimes looked at original pictures that were taken in the field. And this helped us to cleanse that data so that we were working with a really good data set. This is that rate of detection plot that I was talking about. Often rate of detection is referred to by a single number, something like 90% at a particular size. This is expressed in a little bit of a different way. This is a curve that shows how the rate of detection changes with increasing interlinked length of SCC features. This is for one particular tool for stress corrosion cracking features. There are blue dots along the top. Those represent features that were found by the ILI and subsequently found in the field. And then blue dots along the bottom, which represent features that were missed by the ILI and then found in the field. And what you can see is that as you go from left to right, you get a higher density of the features on the top, meaning that as these features are getting bigger, we're finding more of them. That dotted crosshairs represents the tool spec, and you can see in this case that the data we found in the field shows that the tool met the specification. I think, as was mentioned previously as well, that the critical features are likely quite a bit to the right of that crosshairs. So this is referring to the vendor specification. This is a burst pressure unity plot. This is one of the ways that we looked at assessing the sizing accuracy of the tool. There's a bunch of plots on here. I'm going to focus on the middle one at the bottom. So what we've done here is we've calculated burst pressure using the ILI data, and then we've calculated the burst pressure again using the field profile data. There's roughly 200 data points that are on this chart. Data points that fall below that 45-degree unity line, those are conservative estimates, meaning that the ILI tool is calling, if you do this calculation, for a lower burst pressure than you would find if you did the same calculation using the ILI profile. The conservative numbers mean that if you're basing your dig program on this, you're going to find a lot of features that are of a lower burst pressure than you expect just based on the ILI data. The next slide is going to show a couple details of data points and how they work out like this. But as you go from the bottom to the middle to the top, what we've done is we've calculated the burst pressure in different methodologies using different assumptions. And so the top one is not conservative at all. It's pretty much right in the middle. And in that case, we use the absolute depth values that were called by the ILI tool. There often isn't a spec around these numbers, but we wanted to see how they compared with the excavation results. And you can see that in this case, there's very little bias and there's fairly good correlation with the numbers. I will mention one thing as well. We did this with EMAT, and there was some very promising results. However, we didn't have nearly the same number of data points for EMAT. So that would be something that we'd be interested in pursuing down the road in another phase of this project. Okay, here are some example profiles. This would make up 4 of the data points that were found on the previous slide. I've got 3 examples of a conservative estimate by the ILI tool and 1 example of a non-conservative estimate. If you look at the top left, you can see that there's a green line. That represents what was found in the field. There's a dotted line. That represents what the ILI tool called. And so you can see they're a little bit different. There are 2 edges of the curve, or 2 edges of the crack that were missed by the ILI tool. This is the case where if you look at the surface breaking length of the feature and compare that to what the ILI called, you would see a difference there. However, when you look at the burst pressure calculation, you see they're quite similar because the feature shape really matters in this case. So in this case, you have a feature that ends up very close to the unity line on the previous plot. On the top right and bottom left, we have 2 more examples of conservative cases. On the top right, we have one where the ILI tool found most of the feature, most of the length, and had a very close depth call. On the bottom left, we have one where the depth call by the ILI tool was deeper than what was found in the field. And so again, that results in a conservative estimate. The interesting case on the bottom right is one in which the feature is very long and it is also very shallow. So it is just under the threshold where the tool claims to be able to find these features. And so for that portion of the feature, it didn't call anything, but as soon as the feature dips down below that threshold, it does find that portion. But because this is connected to that long, shallow portion, this is one of the non-conservative calls. In this particular case, it works out to about 107% of SMICE. But this gives an example of some cases where the tool seems to be doing a very good job, some other cases where it's sort of bang on, and some other cases where it could improve. I've got one slide to conclude, some of the summary thoughts. The database was selected for long-term industry-wide data storage. Hopefully this can be used going forward to continue to analyze the field and ILI data. Data validation is a critical element in the analysis. We need to ensure that the data is consistent, accurate, and complete. One suggestion I would have is trying to push this validation process closer to the time of data collection. We were doing a lot of this after, sometimes years after it had been collected, so this could be pushed forward in time, closer to when the excavations are done. The correlation between ILI and field measurements are improved under these 3 conditions when assessing burst pressures rather than length or depth as an individual measurement. When more detailed field data is used, profiles as compared to maximum length or maximum depth, and when there is a higher confidence in the field measurement, for example, grinding with a UT measurement. ILI crack sizing can conservatively estimate the burst pressures when conservative assumptions are used. That was that unity plot that we talked about. The rate of detection increases with increasing feature size. And lastly, tool performance varies by tool and is affected by run-specific conditions and should be studied at every ILI run. So this echoes the idea of a management process. This is one of the tools that hopefully can fit into that management process. Thank you.
All right, great, thanks, Jason.
No, you're fine, you're fine. Let me.
So that was, again, one example of how we're using R&D to help improve and drive one of the key initiatives on the ILI program. And this R&D really was data collection and very simply using the existing data that we have at our disposal to better understand the tool performance, give feedback to the ILI vendors, which is what they've asked for. So I think it's a great example of how we can be more effective by taking relatively simple approaches to how we get results from these research programs. So going forward, here's our key focus areas for crack management R&D. ILI technology. So again, ILI project, you just heard about Jason doing substantial work on ILI crack tools, but we also want to look at corrosion, mechanical damage. We've got a database now established that we can populate with industry data, with existing information that's out there, and run similar types of studies. So mining that data is key. Anybody who has any data that you want to contribute and provide to that database, we're all ears. We'll even set up the processes, to make that happen. So we also want to look at improving the current technologies. What can we do? Jeff Foreman asked or made a reference to having access to real-world samples. We're working that issue, and I'll talk about that in just a little bit, but use those samples to define and verify and establish reliability targets for the ILI tools. We saw up on the upper end of the curve, or the top side of the graph there, where we want to be 100% right for the defects that would cause an incident and failure. So let's set that reliability target perhaps differently than we would for subcritical features and other items. And also alternative to hydrostatic testing through that data collection. There's been a lot of discussion in the industry about ILI as an equivalent, maybe not an alternative, but an equivalent to hydrostatic testing, and the engineering critical analysis process that was at least in the versions of IVP that were originally distributed. I guess the most recent one that was around does have a provision for an ECA process. So how can we use the information from ILI to help support that evaluation as well? And we're always looking at difficult to inspect conditions, challenging pipelines that have difficult issues in getting the inspection tools in the lines. Also, NDE procedures and technologies. You heard a lot from Harvey on new technologies that are being developed, but continuing to push the boundaries and the limits for technology and NDE. You've heard also we want to be an order of magnitude better than the ILI tools, making sure that we're there and verifying performance, developing new technologies as well for NDE methods in the ditch. You heard assessment methods and crack growth modeling. That work continues. Quest is doing work. We've got work on ERW seam welds being done by BMT Fleet Technology, and also SCC crack growth models are still being addressed as well. And then we want to look at the role and application of hydro testing. Spoke a lot about that here as well. So let's make sure we understand its use as an integrity management tool as well as post-construction evaluations. And let's make sure that the hydro test isn't causing more damage than good in implementing that study. So some work needs to be done in that area also. And then developing practical operator guidelines. I've mentioned that several times. Highlighted in red here as a lead into the next slide on the API crack RP, but also taking existing information that we have from prior studies, from PHMSA R&D work on the ERW program, for example, and putting that into useful practical guidelines that operators can use to manage the asset. So I mentioned the API crack management RP. You heard from Dave Yisbart earlier today. He broke it down into much greater detail than I'm going to cover here. But again, this is an example of practical operator guidelines, taking a lot of the information that we have, consolidating it and putting it into a meaningful document that can be used on a day-to-day basis. And really using the projects and programs, the R&D work that's being done through PRCI, through API, through PHMSA, et cetera, and really feeding that into these recommended practices, making sure that all that information is integrated as much as possible, and really pushing and driving the projects that matter and can support those efforts. Okay, again, I think at the end of the day, remember, all this R&D work has to support integrity management programs and processes. So, this is a simple diagram showing that process, the continual reassessment and reevaluation of your integrity programs, but applying these technologies consistently across the board for the various elements of the integrity program is key. And we got to always keep that in front of our sites. So looking ahead, key issues that we have to address. So pipe samples are needed, okay? I'll get to the issue of the PRCI Technology Development Center in a bit, but we do need samples from operators. These R&D projects rely on a substantial inventory of materials that are required to run these kinds of tests. They do require destructive testing. In some cases, we have to give up some of the samples that are obtained and used in these studies for the true verification of length, depth, and all the other measurements that are necessary. We also need reference standards and calibration samples. John O'Brien raised the question in Harvey's presentation about reference standards. What are we using to actually calibrate the technology? So some work needs to be done in that area as well. Building the body of knowledge. Again, a great example here by Jason of using existing information. So how do we extract more of that data that operators already have and get active participation to make sure you help support those things? So, you know, the ILI Crack Tool project, I think, is a great example of what we can do and how effective we can be. We also need improved coordination, okay? So we have the roadmaps. I know a lot of different groups have roadmaps, and I think we do need to work more collectively on using those as a communication tool and getting true consensus across the industry, and then working on more of a divide and conquer mentality. I don't think PRCI's roadmaps show that PRCI is doing all the work. We recognize and acknowledge that it's for certain things, certain projects, certain capabilities could be and very well may be now better managed by other parties. So let's make sure we keep track of that as well. And then competition for resources and samples. And that's my lead into the PRCI Technology Development Center, which most of you have probably heard about by now, but this is a big push and a big commitment has recently been made by PRCI to continue the Technology Development Center. This is where we acquire, it's the house for all these real-world samples and defects that have been collected over the past several years, which are turning out to be highly valuable for the development of these technology programs. You know, we've heard a lot about technology performance and how great it's doing. Generally speaking, we're looking for, you know, the more challenging types of features, not the things we know we do well already. So having access to real-world samples, being able to run the kinds of testing that's required for data analytics was mentioned several times as well. Helping the operators on the ILI and the NDE side get better by having access to a set of samples that they can use. So cataloging those samples, tracking origins, fingerprinting them, detailed characterization is all part of this program and helps us have access to the inventory we need to do the kinds of testing on technology development. So big focus in 2014 and 2015 in PRCI's R&D programs. Okay, just some closing thoughts. You know, as always, use subject matter experts when you need them. Bring them in internally and externally. And, you know, back to the integrity management mindset and framework is consider all the factors when using tools and technology and use that as a basis for driving where research needs to go. Know your system. Heard a lot about integrating data. Data integration is key. There's some work being done on that area as well in API. Data integration is something that has to be addressed by everybody every day. When you have changes, identify them and respond appropriately, obviously, and use that information to manage your asset. And also, the last item is let's make sure we define and hold ourselves accountable for metrics for success, which sometimes we overlook as an organization, as an industry. Okay, that's it. It was pretty quick. I'll be here at the R&D Forum. If you have any questions, certainly track me down, or at the question and answer session, you can ask away. Thank you.
Thank you. Next, I'd like to bring up Ernest Lever. He's the R&D Director for Infrastructure at the Gas Technology Institute. He's got 25 years experience. In plastic pipe infrastructures, and he's a mechanical engineer with experience in mechanics of materials and numerical analysis. With that, yes. Come on. What happened to it? Full screen. How do you do that full screen? Full
Good afternoon, everybody. I'm going to be talking about the GTI OTD crack modeling roadmap. So the GTI efforts are related to crack initiation and damage propagation in gas and liquid pipelines are integral to two of our program areas. The first is our risk and decision analysis program. The second is our inspection and verification program. We've spent about $2 million plus in projects directly related to damage propagation that were either completed or initiated in the last 4 years. They focused very much on practical deliverables with solid technical underpinnings. So just a little bit of an overview of what our risk and decision analysis program is. It provides reasons to stakeholders and auditors for decisions related to utility infrastructure design and operations. We employ a multidisciplinary process that includes risk assessment, characterization, communication and management, and the related optimization of decisions. The output of the program includes predictive models, calculators, and databases that describe the complex and interconnected behavior of utility infrastructure systems and their risks. In our integrity verification program, we're developing and deploying inspection and analysis models and technology which allow operators to select the appropriate inspection tools, assess their pipeline systems for defects, and verify their pipeline and fitting material and chemical properties. These technologies and models benefit operators by allowing them to meet the integrity verification process requirements for establishing MAOP and material condition of assets, to conduct recurring integrity assessments required by the code, and also to perform fitness for service of in-service components. So those are the two programs in which most of our projects fall. And I'm just going to go through a couple of examples that we've recently completed or are still busy working on with relation to that. This is a program which we completed recently. It's our leak rupture boundary model. And the need was for a validated model and statistical analysis to develop a leak rupture calculation based on theory, but that incorporates typical industry uncertainty and variability of measurements and provides confidence levels. If you just plug your parameters into the standard equations, there's no accounting for the variability that you have out in the field. So we came up with a technique to explicitly inject that variability into the model and have it reflected in the confidence levels that we giving in the output. So the tool will predict whether the pipe will fail by leak or by rupture based on the material properties and the pipe geometry to assist the operator in determining the consequence of failure for individual pipe segments based on the pipe characteristics. So the deliverable is a software tool with a training manual that outputs a model of failure, the mode of failure, leak or rupture, based on the inputs, the yield strength, toughness, diameter, or wall thickness with a stated confidence interval. And this is based on a full-through wall defect, to speak to Ted Anderson's point from earlier on. So we're looking at a full-through wall defect which already exists, and we're going to say, is it going to be stable or is it going to rupture? We were able to get hold of about 20,000 data points from 14 countries, 4 different continents over a 40-year time frame where people reported ruptures of pipelines. And when we did a very extensive quality control on those, and we came up with 635 data points which we were very sure of. About half of them were actual field failures and half of them were laboratory tests. And when we back calculated those and put the results, overlaid the actual field results over our calculator, it validated our 95% confidence bound. So this is a tool that we think is very, very useful, and it is available now. The second project also in the RDA program is our advanced crack propagation model. And this addresses the increased usage of spike tests and various pressure tests, where there's a concern that the actual test will increase the likelihood of latent damage in certain pipeline categories. So the objective here is to develop and validate a model that correlates pressurizations to crack growth rates, to identify high-risk pipe segments based on historical pressurization records. The deliverable here will be a software tool and associated models with the ability to predict the impact on the pipe integrity of hydro testing and spike testing, as well as select the optimal operating pressure. So this is a very interesting project because we're actually modeling dynamic crack propagation here, and there's quite a lot of sophistication that goes into that to address things like elastic plastic analysis with strain hardening and notch tip blunting, crack arrest, not just crack propagation. So it'll be a very nice tool when it's completed. I know early on we said that this conference we're really only talking about steel pipelines, but this is a plastics project which is actually very interesting in that it shows how we actually do synthesis of data from multiple sources and bring them together into a holistic model which is looking at historic data, environmental conditions, and a lot of attributes of a piping system. It is also very, very similar to the previous project I talked about in that here we're talking about true viscoelastic damage initiation and propagation, which is very, very similar to the elastic plastic with strain hardening models we talked about earlier. So there's probably about 85% overlap between this and a true steel project. And the real interesting portion of it is if we look at the plot on the bottom right-hand corner, where there we're predicting lifetime of a pipeline based on a lot of different attributes that we're pulling in, and we're getting a pretty good agreement. So this is a very good example of how to address the problem of data integration, of looking at more than just what's straight in front of your nose. Another project which we have is enabling alternatives to a hydro test. We've heard a lot of talk about that today. So here the objective is to define the critical flaw sizes and to create critical flaw and metal loss curves for different pipe materials, diameter and wall thicknesses, to identify which ILI tools can detect the critical flaws by comparing critical flaws and metal loss values to inspection tool POD and tool tolerances. And once again, the deliverable will be a calculator that operators can use to select the ILI tools for specific pipe segments as an alternative to hydro testing, also incorporating the methodology into an industry standard. So here you can see those are 4 example projects that we have in our crack damage propagation focus, and we're very much focused on providing a very practical calculator to the end user at the end of it, which pulls together a lot of different information from a lot of different sources. So what do we see as challenges and future efforts? The first is to develop a comprehensive library of pipeline and material properties, true stress strain curves and toughness. This is really at the core of any of our damage modeling. If we really want to get into what's actually happening in the material, we've got to have very, very good true stress strain curves, and we've got to have good knowledge of the toughness and see how we can correlate that and how we can feed that into models which do a much better job of predicting how we will actually initiate damage and how we will propagate it into the pipe wall. So to do that, we have to develop constitutive models that are necessary for viscoelastic and plastic analysis using the finite element method. We really have to get into that if we want to deal with the different tightnesses of material, the different types of material. We want to deal with notch tip blunting. Will the crack arrest? Will it propagate? And can we come up with general models which will address a lot of different failure modes? So the next thing which we have to do is we have to refine our FEM models and make sure that they're capable of modeling brittle, ductile, and shear fractures under any loading and any geometry condition. If we can do this in the same framework, then we'll all be a lot better off because we don't have to use methods and models which are tailored to one specific mode of failure. So those are the major challenges that we see that we need in order to carry on with the pathway which we've taken. So with that, I'd just like to thank FEMSA for the opportunity to participate in the workshop, and I'd also like to thank the Operations Technology Development Company, OTD, for their considerable financial support, their guidance and encouragement. We're very much industry focused, and they put a lot of money into the research efforts which we do. So thank you.
Thank you. Our last speaker is Dr. George Varidis is a senior technology manager with NYSearch, where he manages the organizational's programs related to robotics and sensor technologies for the inspection of unpigable pipes. The one thing that on George's resume is that he's a professor of the mechanical engineering of New York University. I think that is a tremendous asset to share your knowledge with the other students and so forth, and I think that's an excellent position. Here you go, George.
Thank you, Jim. Good afternoon. I'll present to you briefly the research program that we have at NYSearch. related to crack detection, and the focus of our work is unpickable pipelines, for which we have a over 12-year program now to develop inspection tools that will allow us to inspect pipelines that traditional ILI tools cannot serve. So over these 12 years, we have developed a series of platforms that allow us to carry inspection tools in such pipelines. I'll be talking a little bit in greater detail about those tomorrow afternoon with working group 3, I believe, if you are interested to get some more details. But we have developed the first generation of tools that have an axial MFL sensor or an RFEC sensor for the smaller sizes. And at this point, we are looking to develop sensors that will allow us to detect cracks. So as part of this effort, I'll present to you 2 different crack technologies that we're considering. And in conjunction with that, we carried out a study with Kifner that allowed us to establish critical crack thresholds that could serve as the baseline for specifications for the crack sensors that we're developing. Again, the crack sensors are to be integrated in the Explorer family of robots that we have, developed by Airvodane Engineering and commercialized by PipeTel Technology. So the crack sensors we're developing is one, I would call it a traditional one, in the sense that it's a combination of transverse MFL and EMAT. And the other one is a brand new technology that we picked up from a different industry, and we're trying to determine whether will have a value for us, and that's based on advanced anti-current technology. And I'll take you through those 2 in a little bit of greater detail. But first, again, trying to establish the level of detection that we expect from these crack sensors, we carried out a study to basically determine the minimum defect size, critical and monitoring, detection requirements for an inspection tool that would allow us to get an assurance from the measurement that is equivalent to that you get from hydrostatic testing. Okay, so we consider the number of elements, longitudinal and circumferential cracks, variability of pipe material, toughness and wall thickness. Very important, since we're using inspection tools, what is the effect of tool measurement error on the defect size detection requirement? What is the class of the pipeline we're working on? And basically, we took 2 approaches. One deterministic, where we used basically the NG18 equation with some modifications for longer and shallower cracks and for lower toughness materials. And then a probabilistic one. The probabilistic one was made possible by the fact that Kifner has a database of about 750 different incidents for which they have collected a fairly good set of information, and that went into a Monte Carlo simulation that allowed us to really take into consideration the effects of variability of material properties in these cases. So the results have been put together in a normalized fashion so that all pipe sizes and grades can be accommodated. So a little bit more detail on the factors we consider. Again, material variability obviously affects significantly the minimum detection requirement, and we consider 3 categories of ductility, toughness dependent, partially toughness dependent, and then the flow stress dependent, going kind of historically from the older to the newer type of materials. Oops, I went too fast. And coming to tool measurement error, all tools have an error in their measurement, typically specified as a probability of detection. So we took 2 approaches here. It's kind of a little design problem. The first one we approached as establishing the POD for the defect not to be critical. And basically, the minimum defect was defined by the monitoring defect, and then the maximum allowed tool standard deviation was defined by taking the difference between the monitoring and the critical defect sizes for each particular case. And then we looked at it from another point of view, which was what is the detection limit. So if you take the defect and you enlarge it by the measurement error, that defect does not exceed the monitoring defect size, again, for that particular class of material, class of pipeline material and so forth. So I just have one of probably hundreds of figures that you're going to see in our report that was issued lately. And basically, there's a lot of information, but just to give you a sense, the solid blue line is the outcome that you get if you consider no tool error, no material variability, and you just do your the hydro test. And then the 4 lines that you see below that is the corresponding now defect limit, and you see how they shrink substantially for different wall thicknesses, starting from from accuracy in measuring your defect, from plus minus 0.05 wall thickness and going up to plus minus 0.2 of wall thickness error. So you see how the specification drops significantly here. And again, in this curve, also taken into account is the error that you always have in measuring the length of the defect. Okay? Something else, critical versus monitor longitudinal defects. And again, you see it for short and deep defects at the top, the red lines. Again, critical versus monitoring. Critical is the solid line, monitoring is the dashed line. And then the blue lines are those for long and shallow defects. And again, critical versus monitoring. And again, you see at the bottom, this is for a certain grade of materials. So at the end of the study, again, it was very comprehensive. Basically, we don't have one crack defect detection size for all cases, as you would expect. So it varies by yield stress and stress level of the material, the pipe size, how much material property variability you have, and obviously your tool measurement error. But we have been able to put all this together, and for any particular combination of those parameters, we have a minimum defect size that you have to have detected in order to have something equivalent to a hydro test. I'll move on to the 2 crack sensors that we're developing. Again, these are 2 parallel efforts. We're building prototypes of these systems to go on what we call Explorer 2026, which is the inspection robot that can carry out an inspection in pipelines of sizes 20 to 26 inches. So the first one is a combination TMFL and EMAT, as I mentioned earlier. PHMSA is co-funding now this phase of the work, which is basically carrying out a number of field demonstrations and proving the technology in the field. And we were in the process of carrying out these field demos, and we expect to complete them by the end of the year. So this sensor will be commercially available through PipeTel in early 2015. And then there is an advanced steady current sensor, was initially developed for different applications. We picked it up and we're carrying out a feasibility study to see if we can use it here. And that feasibility study is nearing completion, actually in a couple of weeks. And all the results that we have up to now are very promising. So this advanced eddy current sensor has the great benefit for us that requires very little power, and comparing to a TMFL is practically weightless. So weight for us and size are extremely important because we have to put this on a robot. We have to carry all the power that we need to operate the robot with us. So power is premium. So anything small and light has a great advantage for us. So that's what an eddy current sensor is. Of course, this technology has been around for a long time, but the level of performance that you get from an eddy current sensor compared to a MFL sensor is lower, and a lot of that has to do with our ability to manufacture coils, the coils that we use to create the eddy currents, and to a high degree of accuracy. So this new technology called solid-state anisotropic magnetoresistive sensors, they replace traditional coil sensors. They're state-of-the-art. They have clearly superior performance over traditional eddy currents. And the beauty of them is that they can be fabricated using photolithography in linear arrays on flexible sheets. So we can take the sensors and put it on a flexible sheet, and then we can basically give it any geometry we want as we deploy it in the pipeline. So you see that flexible array on the top right picture. On the top left, you see the red circle, that's the coil, and in the middle of it is placed the sensor. And on the bottom right, you can see the results that we got from trying to detect a 5 mil long, two 5 mil long cracks, 100 mils in between the two of them. The one big red circle that you see is what you get if you use a traditional eddy current sensor, and which basically gives you no distinction between the two cracks. And on the right side is what you get with the sensor that we are testing now, where you get a really nice, first of all, detection, and then separation of the two cracks that we're looking for. So we have actually a gas pipe with an EFW weld on it, and we have actual crack defects on them. We were glad to find a company that is actually putting cracks on the pipeline rather than machine defects. So these are actual cracks. It's a proprietary process that they have. And we have cracks that are invisible to the eye. They're 25 to 50% wall thickness depth, and they have a length from an eighth to 1 inch. And we put those cracks both on the seam weld and on the base material, both on the inner and outer surface of the pipe. And as I said, we, with this new family of sensors, we were able to detect all of them fairly comfortably. We get very clear and distinct signals from them, both for those inside and outside. So it looks that this is something that we'll pursue further and move on to optimize them and develop a system that will allow us to deploy them on the Explorer family of robots. And the other one is the TMFL EMAT combination sensor. With our membership, we created a list of priorities, what are the most important cracks for us to detect, what are the least important, and you see the three categories here. Basically, priority one is the seam welds, girth welds, priority two, and cracks on the base material number 3. And based on that, we went ahead to design our sensor. Again, we have very severe limitations of space and power requirements. So a TMFL sensor is inherently heavier than an MFL sensor, so we knew the weight would go up. But this sensor and the tool, they have to be able to negotiate various features in an unpickable pipeline. Short radius bands, mitered bands. It has to be able to be launched through a 90-degree fitting. So the length of the sensor is extremely important, and it's a limiting factor. So going through the design process, we're able to put this sensor together that actually met our requirements, but was only able to provide us with detection of what I call priority 1 and 3 cracks. So the priority 2 cracks, which are the ones on girth weld, they are not going to be detected with this sensor. We have to have something else. So one pass inspection, we launch at one point, we'll come out at another point. We collect the data in that one pass. And extremely important to us, we were able to put the EMAT and the TMFL in just one module. Okay, and it's able to collapse to go through the bends and to be launched and retrieved. And again, it consumes more power. That means that we're going to have a little bit lower range with the robot when we deploy this sensor. So we had to make a compromise again. So the compromise was that we have a full array of TMFL. So basically that provides us the detection of cracks in the base material. And then we have the EMAT that gives us the detection in the seam welds. We went through a whole series of testing in the lab and very recently in the field to determine what is the optimum number of transceivers and receivers to get the performance we want. We have settled that, and the sensor, the final design is completed, and we have put a sensor together, and it's going to have its first live demonstration on September 5th. The beauty of this is that the sensor, if I may go back, you see the sensor in the middle of the tool. Basically, there are two flanges that connect it to the rest of the robot, 6 screws on each flange. So you take out 12 screws, you pull the sensor out, you put your axial MFL sensor on, put the 12 screws on, and you're ready to go. So very versatile tool and operationally very efficient at this point. So where do we stand with that? Again, we have another pipe with, again, real cracks that we tested extensively in the laboratory. We did the first field demonstration that you see on the picture on the top. That was a piece of pipe that was extracted from the ground by one of our member companies, and they made it available to us. They knew there were cracks on that segment, so we went and tested the system. And then we had the second one last week in the test bed that NICERS has in Binghamton, in New York. And we tested the combined TMFL EMAT for the first time with, I would say, great success. And we have 3 additional demonstrations now, live demonstrations from this point on. And the next one, as I said, is next week, and the other 2, next month. And then the other 2 probably in the November, December time frame. So we should be done with this technology by then. It should be in the market for the industry to use through PipeTel Technologies in early 2015. And with that,
You done? Thank you.
thank you.
Now I ask if there's any questions in the audience, and while somebody's walking up to the mic, I want everybody to know that all these PowerPoint slides given today will be uploaded onto the agenda page for the conference page within the DOT PHMSA website. So if there's any questions on what the charts and everything said, you can go back and refer them. So it'll be there in about a week. Any questions? Any webcast? I have no webcast questions. Do I? Oh, we have somebody.
My question's for George on his last presentation. Now, does the robot run through the pipeline while it's in service?
Yes, this is a live inspection.
Okay, and how small diameter could it get to?
What you mean?
Diameter of the pipeline?
Oh, it goes from 6 inches to 36 inches.
Very good, thank you.
Tom Bubenick, DNVGO. This is a question for Jason. I noticed that you used burst pressure on your plots, but didn't normalize by strength. That would seem to be a fundamental problem. How did you handle the differences in strength? Yield strength.
Yeah, the yield strengths were plotted on the X and Y axis using the same value on the Unity plots.
Okay, so the shape of the Unity plot, you've got lower strength stuff in the lower left and high strength stuff in the upper right. the shape of that unity plot is a function of this, the yield stress of the materials. And to look at the models themselves, you would need to normalize that out.
Yeah, okay. On that chart, we plotted the same yield strength on the X and Y axis. So. Yeah.
Any other questions? Okay, this leads us into the, oh, there's a question over here.
Okay, Yong Yi Wang with Center for Reliable Energy Systems. This question is for Jason. When you look at the remaining strength, the outcome depends on the material property as previous caller, also the flaw dimensions and how the flaws are assessed in terms of what modeling procedure is. Or right, when you look at, I guess what you illustrated is that the outcome seems to depend on how you, for instance, idealize actual detected flaw versus assumed flaw shape. So I guess what I'm saying is would that be part of the outcome in terms of assessing the ILI tools? It seems to be your outcome is affected by what modeling or idealization of the flaw you choose.
Yeah. Okay, that's a good question. That's correct. If you think of that unity chart, what we were really showing there is the, we're looking at the combination of length and depth and how it relates to the ILI detection. So we put it into a model and we used the same profiles for calculating the X and Y axis, but we could actually pull that out and draw a similar chart looking at only the combinations of lengths and depths. So that's a good point. This was expressed that way, but a similar chart could be produced looking at only a function of area rather than a function of burst pressure.
Okay, I want to thank this group and
we'll get started here. My name is John Wolfgram. I'm the Chief Engineer with the Minnesota Office of Pipeline Safety. Just kind of going to kick off our last panel discussion here for today. We're going to be looking at kind of a conglomeration of case studies. And our first speaker today is John Kiefner, Senior Advisor with Kiefner and Associates.
Thank you, John. Can you hear me now? Okay. The presentation I have is on crack detection case studies that we looked at as part of a study sponsored by PHMSA. And I don't want to, since there is sort of a negative connotation to some of the things you're going to see, I don't want to give the impression that this is not somehow against inline inspection. And let me put it in perspective this way. When you're all sitting around doing your integrity management for corrosion, if your pipeline is piggable, nobody pops up and says, let's use a hydrostatic test. And the reason is because you have confidence in the corrosion tools. And that's where we need to get to with the crack tools. And I think what we're showing here is it's not quite there, at least at the time we did this study, for ERW pipe, because I have to point out something else that, among other things, you can go to a paper from the 2012 IPC conference, Richard Kanye and others. I think it was basically a Trans-Canada study where they make a convincing case that they're able to handle stress corrosion cracking without a hydrostatic test, and they made a good case for it. In the same paper, however, they did not make that case for ERW pipe, and I think that's what this presentation is about, ERW pipe. We're not saying that it isn't the right tool for ERW, but there's some things that have to be overcome. Okay, how do I punch this thing? Enter? Yeah, got it. Okay. Now, how did we get into this study? Well, the reason for the study was that there was the accident that happened at Carmichael, Mississippi. And after the NTSB investigation, there was a recommendation made to PHMSA to perform a comprehensive study of ERW pipe seam failure issues and to look at, among other things, the capabilities for inline inspection and hydrostatic testing. And this part of it was the inline inspection part. We also recognized at the same time as the Carmichael incident that there were other cases where cracks in ERW pipes, significant cracks, had not been found by inline inspection. So that was the driving force for the study. The Carmichael incident itself, you could argue perhaps that this was a pretty small anomaly, and it was. And it was a 27% through the wall, 2.4 inch long hook crack. At least that's what the consensus of the origin of the failure was. There were probably some disagreements. But anyway, that pipeline was the source of this study, really, that pipeline failure. There were other failures that we knew about, and there are probably more that I don't know about, but one of them, for example, was a 12-inch petroleum products line in which both an ultrasonic crack tool and a circumferential magnetic flux leakage tool had been run, and yet within a year, a 9.5-inch long crack failed, and that crack, because it had been extended by fatigue, was 80% through the wall. Both of the tools had indicated an anomaly at the location, but neither one was judged to be injurious. And I think you'll see some of the reasons for this kind of thing as I go through here. Another service failure was an 18-inch petroleum products line in which the same thing kind of happened. Both types of tools were run, and then a short time later, a very large defect failed in service. Now, granted, some of the defect in a year could grow, but these were huge defects to begin with. So it's kind of hard to see why they shouldn't have been picked up. Well, as far as the study goes, we looked at 13 cases, not representing a whole lot of pipe, but one of the reasons we had a limited amount of data has to do with the fact that it's hard to get data because by the time a company wants to donate data and they pass it through their legal system, they get rejects sometimes. You can't use it, can't let it go. But we did manage to get 13 cases, 741 miles. The range of age of these studies is a little old, but then we started this study in 2011, so we didn't have all the latest and greatest stuff. And you can see the range of pipeline diameters, and then we looked at 9 cases of ultrasonic crack detection tools, 3 cases involving circumferential magnetic flux leakage, and 1 EMAT tool, but as you'll see, it really wasn't a fair test of the EMAT tool. I'll get to that in a minute. This study was done, and it gives you the contract number and the title of the study here. And the phase 1 of this study is complete. Quick summary of the findings. In every case, the tools found crack-like defects. There was no question the tools could find defects. The discrimination as to the type of the defect was not good. And by that I mean, most tools will give you things like crack-like, notch-like, and so on. But what's really needed in ERW pipe is it a hook crack? Is it in the bond line? And the tools are, at this point in time, were not capable of doing that. The sizing accuracy was fair to poor, and in some cases the anomalies, we found sizes upon excavation that were not stated to be detected in the list of anomalies, but were larger than the threshold size. Now, the other thing we found was that field NDE or in the ditch methods did not compare well with ILI measurements in some cases, and we found out that these in the ditch measurements probably aren't as reliable as the ILI. Now, the EMAT tool found anomalies in the seams, but because the primary purpose of the EMAT tool run was to find stress corrosion cracking, the vendor in that case at that time would not provide sizing data. And you can't blame them, they weren't tasked with doing that. Okay, so what do we find? Well, if you go through these cases, you find on the y-axis here, we have what was determined by NDE in the field versus what was called by the tool on the x-axis. And the data on the x-axis are stratified because in some types of tools, you get the data in buckets of size, and we then move it to the deepest size of that bucket. And you can see in this case, the NDE appears to say that the ILI missed some really severe defects. Well, we don't think that was true. That pipeline never had problems as far as we know about after that, so the likelihood is that the field NDE wasn't very good. We found other cases where the opposite was true. Field NDE on the y-axis again, showing that, most of the time the NDE was undercalling what the tool had found. So it goes both ways, and the conclusion is that, well, if you really don't know what the NDE is and what it was calibrated to, it's pretty hard to tell from these kind of data whether that's any good or not. And so the bottom line of that is, as far as I was concerned, was in the rest of the team. And I should mention too that my people who helped me in this were John Beavers and Cliff Mayer from DNV, and they provided some of the data, and I appreciate that. I want to recognize them for that. One of the best ways that we found that when people calibrated what the ILI was doing was to either grind down to the bottoms of defects to really discover the depth, or to do metallographic section. And when you do that sort of thing, then the tool calls start to look a little better. And in most cases, at least in this one case 3, the tool was overcalling the defect. So that's a good result. Bearing in mind that there were still those large defects that cause service failures that cause us concern. As far as length accuracy, usually the tools are a little better on length accuracy, and as far as measuring the length in the field, you don't have to do that usually. If they're OD cracks, and a lot of these were, you can use magnetic particles, and you get a pretty good correlation between length and tool calls in that case. Here was a case where a circumferential magnetic flux leakage tool in which the NDE measurements, again, were saying, well, there's some defects a lot deeper than the tool is calling. But again, because of the particular circumstances of that pipeline, I think it's the NDE measurements that weren't believable in this case. But what it says is that if you run a tool, then, and the only thing you do is NDE, then it's hard for me to say that you can have a lot of confidence in that tool run if that's all you have. Okay, here's one where the magnetic flux leakage tool did pretty well as far as the length that we measured, that was measured, I didn't measure it, by the actual field measurements. So, but what are the other issues that are really important here that we discovered? And that is that the failure stress level in the case of the Carmichael defect would have been greatly overestimated by any ductile fracture model. And that's because this defect, the failure jumped into the bond line and it was brittle. So basically, you've got to deal with that with some sort of a model for brittle failure. And in low frequency pipe and flash welded pipe, that's what you can expect. That's the reality. The bond line will be brittle because of the nature of those processes. Now, conclusions from our studies, the probabilities of detection and sizing and accuracy of the tools were insufficient in these cases to provide confidence in the seam integrity in these cases. The field NDE was not by itself sufficient as a means to validate the findings from the ILI crack tool runs. The tools were not capable of distinguishing between bond line defects and defects in the nearby base metals such as hook cracks. And I think because of the toughness issues in and around the seam of low frequency pipe, we're going to have to get to that at some point where we can identify those two different kinds of flaws. Because, and by the way, this was pointed out by Brian this morning, that if you don't know the toughness of the material you're dealing with, then all the good data you may have on sizing and all your models aren't going to do you any good, because the toughness becomes a critical element. And we certainly determined that to be the case in this study. And that's what it was. We did this study for 13 tool runs, and that's what we came out with. As far as a path forward from this, I'm totally supportive of continuing to use the crack tools. We know that improvements will come. For example, the type of improvement, orders of magnitude improvements that Harvey alluded to with the defect, the NDE work that he was working with. And the same thing happened with electrostatic copying, as we all know at Battelle, when as you see copies come off a copier today at 1 per second, the original model of the Xerox, so which wasn't called Xerox at that time, which was made at Battelle because they sponsored Chester Carlson and with his invention, it took over a minute to get a copy. So things do evolve, and I'm confident that we will see the involvement, improvements to the point where we will have the confidence where we don't have to do hydrostatic testing. And we don't want to do that because you have to take the pipeline out of service. It's not good for short, deep defects. Those can leak shortly after a test. The other thing is, when you run a test, you don't know what you don't know, because anything that doesn't fail could be something that will cause you trouble later, but you don't know about it, and you don't know where it is. With an inline tool, that is the way it works. You can find them, and you know where they are, and hopefully at some point you'll know how big they are, and you'll know how to address them and when to address them. And that's what we need to be working toward. So if we can, I think Brian mentioned that it would be nice to get development of tools that could discriminate between bond line and heat affected zone methods, and we support that. You'll have to, before we get there though, you may have to assume that brittle fracture will occur in a low frequency or flash welded pipe, and in that case, you're going to end up coming up with having to dig a lot more defects. So we need to get better, because that is an expensive process if you have to dig up everything. And I think that is the end of my presentation. Thank you.
Thank you, John. Our next speaker is Sean Keene, Senior Manager of Integrity Assessments, Pipeline Integrity with Enbridge Pipelines.
Hello, and thank you for the opportunity to share with you today. Enbridge has a long history of managing crack threats on our liquid pipelines. We have lots of successful programs. Our program is huge. They're applied to a variety of different pipelines, covering 40s vintage through modern construction. We have every kind of coating and every kind of seam type. Low and high frequency ERW, flash welded, submerged arc welded. We're a complex system, and some of our pipelines operate aggressively. We have every kind of integrity flaw, and we have comprehensive integrity management programs to deal with these. And these programs have run successfully for a long time. In 2010, we had a failure at Marshall, Michigan. That is the most profound failure we have ever had. We were a good company where bad things went bad. And from this event, we had significant learnings. Our whole management system had to be checked. We discovered that, at the time, we were over-relying on technology, and we needed to have an increased focus on uncertainties. And by technology, it's not just inline inspection. We're talking about many types of technology that contributed to the failure. Fit-for-purpose calculations, data management, our training, everything. We learned that effective crack management is the integration of all these layers of defense. We also learned that we needed to take a longer-term view of our integrity management program. And we now drive for infrastructure decisions with a 20-year outlook. The other thing we learned from Marshall is that we can't rely on the pipeline industry standards alone. And now we are starting to review other infrastructures like avionics and nuclear. We're pushing beyond current approaches. Our goal is 100% safe operations and zero incidents, and we continually strive towards that objective. Over the past 2 years, we've invested more than $4 billion in the maintenance and enhancements of our pipelines, right across our operations. Our investment, combined with the commitment of each member of the Enbridge team to make the safety and reliability of our operations our top priority, helps us to safely deliver the energy that we all count on. And we're sharing the associated learnings with industry so all can benefit. Crack management is a program. It's not about selecting a single nuanced approach. It's not about crack ILI versus hydrotest. It's integrating all of these. It's about reliability analytics and making decisions based on these. Pressure reductions may be necessary. Additional ILI may be required. It's about achieving a reliable infrastructure, and how it's achieved is dependent on the personality of the pipeline. Data and analytics form a key aspect of an effective crack management program. They form the basis for the seam susceptibility assessments, condition assessments, identifying and defining uncertainties, and significant resources are required to integrate the vast amounts of data and analytics and formulate these into plans. We now have 180 focused engineering positions to manage the integrity programs, plus additional resources within other groups indirectly involved in integrity activities. That represents close to a 300% increase in human resourcing since Marshall. These teams are working in specialized fields, and our training programs have developed alongside. Competency and learning maps are becoming formalized. History is a powerful tool, and our event learning management systems have been strengthened to facilitate the knowledge transfer from past events. We have become very aware of our safety culture, and process safety management forms the background for all of our integrity work activities. Last year, Enbridge employees and contractors made over 59,000 proactive formal safety observations to identify and address unsafe conditions, actions, or to recognize and acknowledge safe behavior and situations. The analytics completed by our teams include a focus on crack inline inspection technology. And right now, we find that inline inspection is working. We've run 250 ILI tools last year alone and completed 2,600 integrity digs. And we assess crack ILI program performance as part of every dig. What we find is that the newer generation tools are advanced since we had Marshall. The POD is approaching 100% on many lines, but not always. And so the crack ILI technology must be integrated into a system to identify and manage this aspect. The PRCI evaluation of 80 recent ILI runs across industry is the largest compendium and analysis of the current crack ILI technology. And it demonstrated that the current crack ILI technology can be used to identify the pipeline anomalies that matter. Through the high volume of investigative excavations conducted for reasons other than crack ILI, we've seen that there is a low likelihood of unreported threshold features. We've also seen that the application of recent advanced ILI analysis methods has led to the identification of many features smaller than the stated thresholds. And this observation was also echoed within the PRCI evaluation. Recent Enbridge experience on a low-frequency ERW line found a number of very short but significantly deep manufacturing defects that were shown through metallurgical analysis to have been present and undetected through a recent hydrotest. These defects were also below stated ILI thresholds, yet were identifiable through advanced ILI signal analysis by the vendor. Recent ILI technology is achieving high performance, and most limitations of ILI can be managed. Some lines may require more than one single inspection program to address the condition. The right tools must be selected, and managing parameters such as the line flow rate, cleanliness, etc., are all essential to the success of the program. Choosing the right tool means ensuring the capability of the tool matches the requirements of the program. For example, the reliability of the program can be significantly impacted by the critical crack size for the given pipeline. Thin-walled pipeline operating at high pressures will have a critical crack size that approaches the limits of some tools' ability to reliably detect and size. Crack ILI is only one of the many layers of defense that comprise our crack management program. Fit-for-purpose calculation is an important component and requires the use of data that are often subject to considerable uncertainty. There are distributions associated with the input parameters. Yield strength and toughness are commonly discussed, and wall thickness also has a distribution beyond discrete nominal values. The use of extreme bounding values for the relevant parameters can lead, in some circumstances, to unacceptably over-conservative predictions of structural integrity. Fit for purpose is just one component of a multi-component program, and applying extreme bounding values within many components further amplifies the effect. We know there is uncertainty and use risk assessments to heighten our work in certain areas. There's a variety of strategies that we can do for crack management. We can smoothen out pressure cycling by optimizing operational practices. Pressure reductions can be imposed. Further performance verifications can be completed, or a complementary ILI can be run. These are just a few of the options. Enbridge takes a life cycle approach to managing integrity. It begins with integrating pipeline integrity requirements into the design of the pipeline routing, the coating, the pipeline steel, operating philosophy, all facets that ultimately form an integrity barrier. As the pipeline ages, we have tons of diagnostics to monitor pipeline condition, and crack RLI is a powerful tool. These diagnostics allow us to make very powerful long-term infrastructure decisions. It's these diagnostics that allow us to make a convincing argument for replacement. And it's the reason that we are now replacing two of our most significant integrity concern pipelines, our Line 3 and Line 6B. It's these diagnostics that enabled us to build the case for replacement. Our Line 3 is a cross-continent tape-coated pipeline that we have had integrity challenges on. We know we can continue to manage it with ILI, but because of the data we have, we know it's not the most effective approach. This line is better to be replaced than maintained. The diagnostics allow us to connect with our management, our customers, our regulators, the public, and our investors. Crack management is a program, and there is a strong list of program components that can be further developed to enable efficiency to achieve and to demonstrate program reliability. The next generation crack tools will increase reliability of characterization, human factor, and Enbridge is working with vendors to develop the technology. Field NDE needs to be thoroughly addressed, and we're supporting the IOX work that Harvey presented on earlier. Reliability analytics for all aspects of the program need to be defined and promoted. ILI vendor performance specifications need to be written in terms of pipeline reliability as opposed to detection thresholds. And the PRCI Technology Deployment Center is on its way to becoming a place to demonstrate or qualify that performance. Significant efforts over the last several years need to be transparent and shared. Current best practices are needed, and API has taken steps to expeditiously develop these. Regulations should support best practices. We need involvement of all stakeholders to achieve social license. We believe crack management is achievable. We have the technology, we have the capabilities. It requires integration of all the parts. It's not one thing or the other. Companies can demonstrate good programs, and we can demonstrate good programs. Decisions should not be arbitrary. They should be based on data and evidence and reliability analytics. We don't think a single nuanced approach should be mandated, but instead what should be mandated is effective integrity management, and recognize that each operator has their own approach. An API crack management RP can provide a framework for enhancing that approach. A program may be line-specific or system-specific. After Marshall, we are committed to sharing, and that is our goal. Enbridge has expended significant resources to achieve learnings, and we're sharing our learnings with industry so all can benefit. I'd like to thank PHMSA for the opportunity to participate in this workshop. Thank you very much.
Thank you, Sean. Our next presenter is David Warman, Senior Manager of Pipeline Integrity Engineering with Enterprise Products.
Good afternoon. I'm going to change up the
topic somewhat in the fact that we've talked about a lot of inline inspection. I'm going back to a section of our pipeline, one of our sections where we've, since the integrity management programs come into existence, we have been managing, and this is just a component of our system, this section with hydrostatic testing. And we've had, it's an 83-mile section, high vapor pressure system. Here's a map of the enterprise system. We have over 40,000 miles, probably 50,000 miles of pipeline throughout the U.S. And I'm going to give kind of a summary before I go into this. As I stated before, this is a 12-inch pipeline, and we've been doing the integrity testing for the seam fatigue failures based on hydrostatic testing. We have not, and I just want to make it clear, we have not seen any SCC on this pipe segment. Hydrostatic testing was performed in 2004, 2009, and 2013. And in summary, based on those hydrostatic tests, we have had failures. All of those failures occurred at pressures greater than 90% SMYS. We did get some pressure reversals, but in none of those instances was there any fatigue growth measured on any of these failures. As a summary of the pipe attributes, 12.75 250 wall X52. It had at the time it was manufactured back in 1961, it had an API test of 85% of the SMYS, 733 PSI. Lone Star, low frequency ERW, so it's vintage pipe. The pipe was normalized to 650 degrees Fahrenheit, that's good. And it was installed in 1961, so it's 53 years old. And at the time it was installed, it was pressure tested to 1600 PSI, which represented 78% of the SMYS. And the nominal operating conditions of this pipeline is 1440, or represents about 70.6% SMYS. And on this section, there's been no in-service ruptures. In 2004, we did our first set of hydrostatic testing as part of the integrity management plan, and there was no test failures. The actual testing philosophy back then was about a 1.25 test, and so the actual pressure test range was 85 to 90% SMYS. And 5 years later, we pressure tested again in 2009. In this case, we took a little bit more aggressive look. We said, let's increase and so that we get all the pipe segments above 90%. And we did have 12 test failures, 6 hook cracks, 3 stitch welds, 2 low ductility bond lines, and 1 cold weld or lack of fusion. Once again, we did not observe any fatigue on any of this pipe or any fatigue growth. And then the last test round, which is in 2013, we had 6 test failures of the seam, and all in the seams again. This time all the pressures were above 94% SMYS. So our testing philosophy was once again above 90%, less than 100%. And you can see we had hook cracks and interaction of hook cracks and stitch welds. And based on sending it to the lab and getting the lab results back, once again, no observed fatigue growth on any of these. And this is just kind of giving you a look at the test sections that were tested. And this is, you can see the actual pressure profile along the test section. And if you look at the blue line, that was a test that was done in 2009.
You can see that in 2013, we matched a lot of that. And the blue dots represent failures that occurred in 2009. And you can see that some of them are below the test pressure we performed, but that's not necessarily unusual because the previous hydrostatic test was lower than that. It was about, on average, 154 PSI lower. So what we're doing is we're failing seam defects that have been there since day one. And then 2013, you can see the red triangles. Basically, in all cases except one, they are matching the hydrostatic test pressure. There was one there that failed at 13 PSI lower. That one did actually get to the higher pressure, then another section failed, another section of pipe failed, and then when we repressurized it up, it did fail at a lower pressure. So we saw a pressure reversal on that. And this is just the summary, once again, of the milepost, the failure pressures, and you can see the range anywhere from, basically 95% SMYS and up. And they were all ruptures. And in some cases you saw, there was one on the far right-hand side where you saw the pressure reversal at minus 13 PSI. In a couple other cases you saw it was higher, 59 PSI, higher than the previous hydrostatic test. And that was, we readjusted some of the test sections so we could test it a little bit higher. So that one where it's failing at 59 PSI higher just happens to be that we tested it higher. And so we're getting more of the original flaws that were defects that were left as part of coming out of the mill. And you can see on my notes, I've already stated 141 PSI higher than 2013 was in 2004. And the target pressures were increased to extend the fatigue life because we did the traditional fatigue life analysis. But that's where I'm going to get into the next step. Okay, what did the fatigue life of this pipeline look like? Before I get to there was Kiefner Associates put together, they looked at this line extensively and they looked at some of the pressure reversals that occurred during some of the testing. And this is based on a larger population, not this section, but you can see that in this case here we had a pressure reversal about 13 PSI, and if you look at this graph, you've got an 80% cumulative probability that no pressure reversal would exceed 16 PSI. And that's just some useful stats on this, saying that yes, you can get pressure reversals. You may get one as high as 92 PSI, but you got a very low probability of that occurring. When I went back and looked at the failures that occurred in 2013, a lot of them are hard to put into a failure assessment diagram. There was a couple that was a OD hook crack matched with an ID hook crack. I didn't want to get into that. Makes it a little bit difficult to model. And there was some stitch welding associated with hook cracks. So what I did is I said, let's look at one that was a pure OD hook crack, and it was measured 4 inches long, 100 mils, which is about 40% of the wall thickness. And the yield strength, the actual yield strength in the seam was 61,000, and this was X52 pipe. And we had 2 Sharpie V-notch upper shelves of 20 in the body and 9 in the bond line. That's assuming they got right in the bond line. And if I use the modified log secant formula and put in those actual pipe attributes, we can actually see, if you look at, I've actually put the pipe attributes in, you can see the blue line there is for the 1440, if it was at its MOP. You can see the red dot there represents the actual flaw that failed. And I've also reproduced the curve that came from the log secant formula for 1936, and actually it
predicted it very well. And I've used this for many of the hook cracks on other anomalies on this same pipeline, and quite often I get a very good match. And if I don't get a match, it's not that far off. All right, when I looked at the same hook crack and I said, well, this is a good one to do. Let's plug this into the fatigue model. We know the world's not perfect, but let's plug in this length and this depth, and let's take an actual snapshot of 1 year data, and let's extrapolate that data to this actual point, and do a fatigue analysis on it and see what would happen. And remember, this flaw has been there since day one, so it's been in service 53 years. When we ran the fatigue analysis, we got about 42 years for it to fail, and you'll see that it failed at 1,084 PSI, and that's because that was the actual pressure spectrum. It's going to run it through until it hits that high pressure. Where it was located, it's about 30 miles downstream of a pump station. That was the highest pressure it saw. That would be about 42 years, with a final depth of 72% of the wall thickness. And then I reran and said, okay, well, let's run it until such time as it would fail at its MOP. And that was 34 years with a final depth of 60%. So if the model was accurate, then we should have seen a failure here. But what's even more, and we know there's conservatism built in there, but what I would have expected to see some type of fatigue growth, and I haven't seen any. This is showing it should have grown, and even though if you've got some boundaries there, it just hasn't. So as I say here, there seems to be some compounding effects. And this is where I think we have to be careful sometimes when we do these analyses. And what I wanted to step back, and I want to point out there's some research going on looking at the constants in the Paris equations, specifically for ERW welds. But some of the potential conservatism in that is we do use Enterprise has been using the API 579 crack growth rate. As you can see here, it's 8.61 times 10 to the minus 19. There's other out there that can be used. Another one we've seen published is 3.6 times 10 to the minus 19. So the difference between those two models is a factor of safety of 2.4. So if you use the other model, you would get 2.4 times longer life. And the other thing we have to remember too is when we're using these formulas that people have put in API and other ones, they're not based on the mean. They're based on the mean plus 2 standard deviations. We're going, and they should be, but remember there's conservatism built into that model. And I looked at some of the data out there, and from a mean to that 2 times the standard deviation, there's over a 2 times factor of safety, and sometimes it can be much larger. And then the other one is what do you use for a crack size? There's reports out there, some good reports that indicate that the fatigue cracks that are observed are anywhere from 1 times the square root of dt to 4 times the square root of dt, with 2 times the square root of dt is kind of a good average out there. And you can see if one uses the lower bound, 1 times 10 to the minus dt. So if you use that lower length, it gives you a greater depth and it gives you a shorter life. And there's a factor of safety there of 1.4 if I apply it to this. And quite often when we do analysis, we're using the pressure spectrum right downstream of a pump station. And the reality is, once you get far enough away, there could be some differences, but quite often the spectrum is going to be a lot lower. And in this case here, if I use this at this location, if I was to apply the actual pump station pressure spectrum versus the one at the site, there's a 2 times factor of safety. So in all that, there's a potential in this of over 17, a factor of safety of 17 times in the life prediction. I'm not saying it's going to be 17 times, but it could be up to that. You got to remember, and then on top of that, you know, the industry likes to add a factor of safety of 2 on that. So now, when you look at that, we've got a factor of safety that could be as high as 35. You know, this is one thing we have to be very careful on. You know, we're managing our systems. And I look at doing this hydrostatic testing program on here is a good integrity assessment. But at what cost sometimes? You know, if I'm getting something that's saying it's a very aggressive spectrum, or it's an intermediate, and I'm applying these factors of safety and it tells me I've got to test them 4 years or 5 years, when maybe the appropriate timeline's 10 years or 15 years. To test this pipeline section, I've got to take it out of service 1 month every year, and I've got to stagger that along the pipeline system. I'm impacting people for being out of service. So we've got to be very careful on what parameters. And I've seen some of the research out recently of how we can make things more conservative. And I want to make sure that we just don't keep going down that road. You know, we hear some, well, maybe we should be using these factors, these other lower bound factors. Well, what are we doing? We're making this so conservative that we're spending so much time and effort on this, when maybe taking a step back and doing this less often, right, is a better idea, and use your resources to spend time and effort on other pipeline segments. You know, here's some of the conservative failure predictions for this line that have been used. And just to give you an idea of a difference, if we're using the pressure spectrum at the pump station and using the depth of a 1.8 inch crack, which is equal to 1 times d square root of dt, you're getting about 20 years. And if you use the 2 times, there's an error there, it should be 2 times the square root of dt, it's about 31 years. So I guess in conclusion, you know, what we're seeing based on the hydrostatic testing, that based on our current pressure spectrum, how we're operating this pipeline, there's not a significant threat of cyclic fatigue going on. And on this segment, you know, there's been 53 years of service on it, and we haven't had a fatigue. We haven't observed fatigue. And going back, you know, with the second and the third round of hydrostatic testing, I've said that I've called this the spike pressure. You know, that's kind of a gray area. We had that discussion earlier today. We call this a spike pressure because it was higher than what's the qualifying test, but it's not the range of 100 to 110%. And I also want, you know, as I stated earlier, I'm concerned. In this case here, we're managing this pipeline fine without testing it to over 100%. And I don't suspect that it's going to, as long as we keep a good active management program on here, we're going to see failures due to fatigue. While I love to test it to 100%, I know if I tested this line or other lines that have vintage over 100%, I'm going to start seeing a lot of failures. I'm going to be blowing up pipe in people's backyards. I'm going to have hundreds of failures. So we've got to be very careful how we define a spike test. I think I've said everything else here. Let's see. It was concluded that various conservative factors applied is reason for no observed growth. In some cases, it can be as high as 35%. So, the conclusions here is let's take a look at some of the factors we're putting into this so we don't have it overly high factor of safety in it, so we can manage it appropriately. And you know, the good news is we've got 3 hydrostatic tests. We can do some work, and we can confirm with some of the industry that they're doing now, looking at some of the C and the constants for C and the power, how this could be more effectively managed and get more realistic numbers. And you could say these excessive factors of safety don't always improve integrity of the pipeline. I mean, we're getting some pressure reversals, not significant, but we are potentially doing damage to some of these flaws are there. And maybe, in our case, one of our considerations is maybe not testing on a 5-year frequency for testing. You know, let's look at inline inspection. I know John did his presentation earlier. I mean, inline inspection for seams are getting better all the time. And I think we've all seen that. At Enterprise, I've been there a very short period of time, and we're doing 200 assessments a year, and we're doing the whole range of MFL, TFI, EMATs, we're doing CDs, and you know, it's amazing what you're finding. So we're getting good results. And I think kind of staggering that type of thing is probably a good thing to do. And then one last note, it's not on any of my slides. It's when, you know, it's one of my concerns about the integrity management rule that says once you assess something and it's a potential integrity threat to your line, it's a 5-year cycle, it seems, or less if you can't prove 5 years. So if you do a fatigue analysis on a line that says it should last 20 years, right, from a seam susceptibility, and I take half of that, why can't I say in 5 years it's not a threat, but in 10 years it is? And why can't I do my integrity threat in a 10-year basis? Anyways, it's just something to throw out. I think sometimes we get ourselves boxed in. Once we're there, once it's in the box, how do we get back out of the box? So we can spend our money on risk reductions elsewhere. Because let's face it, it costs a lot of money to do a hydrostatic test, and it's very disruptive. And if we can find the better tools that extend that, and we can spend those resources on a better risk reduction somewhere else, that's where we should be spending. Thanks.
Thank you. Our next speaker is Dave Katz, a metallurgist with Williams. And then we have a few questions from our webcast participants, and we'll hit those here after the last case study.
Hey, I want to thank John, Sean, and Dave for some excellent presentations in this panel. I will attempt to meet this high-quality standard. Before I start, Dave Katz, Williams, as Ian brought up, given the short notice I got to get up here, the good news is the lawyers at Williams really haven't vetted this. So anything I'm saying up here today is my personal opinion, not to be misrepresented as the Williams shareholders' opinion. So Larry's in here also. Larry's my supervisor. We've gone through a few changes at Williams lately, and we're getting a little more involved with midstream. So it was good to hear, Dave's fatigue analysis on these high vapor liquid, because we're using the same approach really on the natural gas side for a good part of our system. So I'll kind of give a natural gas transmission take on this. We've heard a couple liquid and high vapor pressure lines. And really with the focus on this is just the crack management side, pipe body and seams. And it'd be a little bit of tint from Northwest Pipeline, the western part. We've got some work going on at Transco, and then Gulfstream. So you may know that part of the Williams companies. I don't have the usual slide. And then we've got a lot of midstream assets up in the Marcellus and Utica. But our first tool run was back in '94. One of the problems we had out west was we basically had to install launchers and receivers on really everything and change out the valves. Any of the older pipelines that weren't built to the standard that we've got in the code later on to mandate them being piggable. So we did have a bit of a safety culture step change was required when basically we're going in and saying we want a couple million per line to put in pigging facilities and then change out every valve to the tune of $250,000 per valve. So it took us a while to catch up. The good news is the safety culture I see going on at Williams has improved significantly from a legitimate question. How long is this going to cost us in 10 years? This was well before the IMP program rolled out. We were trying to convince ourselves ILI was the way to go, and I would argue a little bit my 15-minute presentation to show we've come a long way working with Company G, with Jeff presenting, and Company R with Thomas Boyker presenting. We've come a long way. We've got TDW out there closer to my house in Salt Lake that's come a long way with some EMAT tools, some spiral technology, multiple data sets. We've seen a lot of progression. So basically this is boiled down to 35 ILI runs we have pretty much focused on CMFL with some USCD in there early on in the 2000s, and then EMAT as we evolve that technology, especially on these lines that Richard likes to call problem children or special lines. So since 2001, our first USCD run in a liquid slug, keep in mind this is all gas pipeline. We began really intensively running. Sergio and I looked at the pre-70 ERW on our system. It's almost half our system. You know, out of 3,000 miles out on the northwest side, we've almost got 50% is pre-70 ERW. Some EFW mixed in there. Big problem we had is I got to get through those 1.5D bends. You know, we heard from NYSERC, you know, they got tougher than 1.5. They probably laughed that we got to get through 1.5D bends, but there's not a whole lot of CMFL tools on the market for 1.5D because you're turning that magnetizer sideways. A lot of this focus has been Washington and Oregon, Pacific Northwest. I'm not looped. I'm pretty hilly. Hydro testing is going to be kind of tough, especially if I'm on the other end of the burner tip in the winter and you're hydro testing my single source into town. I'm going to get a little upset, and I will gladly notify my local senator and representative. So Idaho, also in Colorado, and we've got some good recent results out in Virginia. Most of this smaller diameter, but not exclusively. So the other key I'd like to bring out, we're not going to get into it, but the EMAT and CMFL, and you'll hear that from TransCanada, the EMAT coupled with the CMFL is really what we started to look in pipe bodies early on, 06 to 08. We're finding the seams, we're getting a lot, very encouraging results with ERW and EFW seams combining the EMAT with the CMFL. Now again, you got to go back to the safety culture because let's face it, that's a lot of ILI costs up front to get into a pipeline. So rough tallies, how much are you talking? We're not as big as Enbridge, and I like seeing what Sean has done because they have gotten very aggressive and have been aggressive. And it's good to see because we've all learned a lot from the USCD work that they've done. And we've got about 1,300 miles now ILI under our belt, some repeat runs, 400 excavations, you know, a fair number of composite repairs where we're not finding that much, but it's cheap insurance. If you're just finding, you know, that it's lack of fusion, let's just stiffen it up and go on. A lot of these Petra sleeves we use is type A, where we've got surface breaking internally, sometimes surface breaking internally and externally, and mid-wall laminations that you're reflecting with using a phased array. So these compressive sleeves we're pretty comfortable with. It's not a sales pitch. I don't work for Bob Smythe. But we really like those. The welders like them, and if we can get 5 or 6 holes open, they can come in and put them on, and we go about our business. But we also have got 93 cutouts in there. Not really well received in even when we're digging in the summer. If you're not looped, you're looking at a $500,000 to $1 million stopple bypass. The kicker we've got is, and I'll show later, burst testing really backs up the fact that a majority of these indications that we're finding are resident. I like that term, resident. You know, they're not stable. I'm not stable. Ian brought that up too, cracked. We're talking about cracks. So, you know, non-injurious, and they're non-injurious over the short term and the long term. So how did we build the crack program? Sean alluded to it. It's got to be comprehensive, and we learned that the hard way. We sat through some rough audits in '06 and '08 with our integrity management program. We needed to do a better job, and Williams took that under advisement from our friends at PHMSA and our friends at several state regulators, because I know we've got the state regulators in here. We had it there, but the safety culture change really pushed that. There was no questions asked. And the blank check was pretty much given to us for quite some time. So we built that on choosing the right tools, understanding the fatigue-related threat. You know, that's key for gas pipelines. We're not immune to it. We just know the cyclic loading, if you do your homework, and we can pull SCADA data now and look into it, you can show that a 5-pound increase over the last prior 5 years to the present 5 years does not a new threat make, and we've presented that and gone about our business through our audits. The kicker, though, is you've got to confirm it, and we heard Jim Marr talk about this, and I like that presentation. We've got to confirm these ILI calls with accurate, reliable NDT in the ditch. No questions asked. Were we there 10 years ago? 20 years ago, we went up to Jim, we bought fixed transducers, or we tried to. You could buy 3 or 4 different angles. That's all we had. We didn't have phased array. It was still on the drawing board. We had to go down to Southwest Research, and they kind of wanted to see our passport and security clearance and wonder what the hell we wanted to do with these fixed transducers. So it was a pretty tightly controlled technology. Now we're with, all of us can get phased array units. The kicker's going to be how accurate is the individual working the unit. We heard that from Jeff. The tools are doing a good job. It's the human-machine interface. The weak link probably ain't the machine side, it's us. We'll talk more about that. Sean's got some good work we're doing at the Technology Development Center with how to speed up, how to make phased array more accurate. But we're sold on the phased array. Certainly we weren't 5 years ago. What else is up there that you haven't read already? I think I'll go to the green, because I think that's probably a kicker. One of the issues are you're going to have some high and low relative risks when you run these tools that may not correspond to your initial risk assessment. Once you've run these ERW, you know the ERW threat's there, but when you get some of this ILI data back, don't be surprised that some of these problem children cause you some heartburn, and they should. You know, a high consequence, high likelihood of failure probably pushes you to replace like we had to do. We've got about 22 miles now we've replaced since we started this CMFL program on vintage 16-inch ERW from the same manufacturer Dave had spoken about, which is Lone Star. Lone Star seems to be problematic for us, but not that it was a bad process. It's just, you know, some of the QA, QC that we've got now wasn't present back in this is mid-50s. We don't always have post-well heat treat on some of our pipe. So 2 sections of line in Oregon City were replaced in Spokane, but it was after 5 to 8 years process, which included hydro testing, which included some significant burst testing, but we were able to safely manage that with ILI. Large amount of the 26-inch you may be aware of was DSAW. Capacity was replaced in 2006. A lot of that was pipe body cracking. But all along this way, PHMSA West Region, you may remember Ed Ondak, you know, prior to Chris Hoydell. Ed and Chris have really been our biggest proponent out west in working hand in hand with us. Sometimes we's not here. Win was going to be here from West Region. He couldn't make it. We was in the ditch with representatives from the Washington Utility Commission while we were digging up our first Rosen EMAT digs in the gorge. Was there a little consternation from my management at bringing PHMSA out on the dig site? Yeah. But I think, again, the safety culture that we've kind of inoculated everyone with was like, okay, makes sense. So the learning curve there, I think, that we've done is really working hand in hand with the regulators, state and federal, plus the ILA providers. You know, both GE, or Company G and Company R, have provided analysts with us in the ditch to work with our NDT reps. And that's been key to keep the data flowing. Jeff brought it up, and so did Thomas. So, pictures. Jim likes pictures, I like pictures. You know, yes, if we look close enough, will we find some lack of fusion out there on this pre-60 ERW? Yeah, and if you look at the scale, 10 microns, I am not gonna go worrying about a 20 micron length, quote unquote, lack of fusion. A lot of the testing we've done, a lot of the metallurgical sections that people brought up that we need to do, there's no arguing that. But a lot of what we got out here in this pipe, even though it's not post-weld heat treated, is this blocky ferrite is probably giving us what you're gonna see in these burst test tables in a few minutes, is giving us this higher fracture toughness, allows us to assume a little higher than 4 foot-pounds in the long seam. And I think the data shows that with the burst testing. And as a side note, what you'd expect to see in some of this non-post-weld heat-treated area right here in the long seam, you'd probably expect this more brittle acicular or for the Germans in the audience, the Widmanstätten ferrite. So that blocky ferrite really is what's giving you the properties. So this next one down here, and we'll show a little more about 69, you'll see that joint 6930 and see what the burst test was, but if you look down there below that joint 1300, you know, it doesn't take a rocket scientist to look at that one and say that black stuff looks like it's nearly through wall. You know, we talked about through wall, leak versus rupture, stable versus unstable on the API 579 FAD. But the kicker here is, if this is a cold weld and it burst tests at 1360 and it's 85% of piece mice and I'm operating at 896, I got plenty of safety margins, similar to what David brought up. I think since we're working on the API RP for cracks, this, maybe we should coin a new term, because this cold weld, if it's gonna stand up to 1360, maybe I'll call it another kind of weld, and I'll get to that bottom one. Weak bond line, yeah, I mean, if you look at the grain size, that's a weak bond line, but it's testing to 1754. There's 108% of smice. So I'm calling it a lukewarm. I think those are lukewarm welds. They're not cold welds. That's just a term for the API guys to work with. I did want to put in the proverbial hook cracks, because we do have them in the gas industry. TransCanada's seen them, we've seen them, but they don't seem to grow too much under fatigue loading, and it makes sense when you do the fatigue analysis. But this, the one up there with the non-injurious hook crack, I'm calling about 15% of depth. It was in there in 1956 when Lone Star rolled that steel. Burst at 1889, 116% of piece mice. This is some 20-inch over there that's just at 4x, but we've got, you know, are there cases where we're gonna get, even in the gas industry, if that hook crack interacts, you know, with a lamination that's, you know, pretty dense, you can have some issues under low fatigue, cycling loading, even with natural gas service. Holler at me how we're doing on time. Here is the 24 joints, burst tested. I'm not gonna expect you to read where joint 1300 is. But what it says is part of your program does have to be getting out there. So I don't understand that much, but I do understand if we burst test it, you can record a pressure, and it gives you a pretty good idea of what safety margin do I have out there on the pipeline, because the guy living or gal living on top of us in the right of way doesn't really care whether it's near neutral, classical pH, a hook crack. They just want to make sure they're safe living on our right of ways. But what this boils down to is, again, 24 burst test joints, all with some significant features you saw. Really no issues that I'd feel uncomfortable with running the ILI technology. Are there going to be some short defects that we're not going to find? Will they leak? Yes. The answer to all that is yes. These tools are not infallible. Next is, you've got a couple, like we said, the NDT in the ditch. Really, we've seen the phased array is very critical to verify what the ILI tool is picking up. Early on, we were just beating our heads. But between 04 and 06, it was going to be tough for us to even, we were cutting our teeth on phased array. And if you're going to couple that with cutting your teeth on deploying new technology, you can create some headaches for operation pretty quickly. The kicker here, I think, is the continuous improvement loop is really linked in with the the ILI expertise in the ditch has got to be there with us, with our ILI, vendor. And the two we primarily use, there's just two we're comfortable with. And within those two companies, there's probably only 5 folks that I'm going to be comfortable with if they call me at 10 p.m. that I trust what they're doing. So we have brought up, that there's some work we need to do on the NDE side without a doubt. One of the things we've done to speed up, because I'd like to look at all the long seam we can when we're in the ditch, we've really started with this encoding module. You really can see the level of detail I've shown here on the phased array scans. What do we need to move forward? And that's what Bob asked us to do. And I will take a break to the web audience. I took a break for water. Really, I think what we're looking at is continued long-term funding of this. You've heard this already, this Technology Development Center. The Technology Development Center, I think, is going to link quite directly with our joint PRCI PHMSA ILI pull-through facility that we're going to need to really take our samples that we've characterized very well, run the ILI tools through there, and prove up 90% of what we can find is going to be very clear, I think, with those pull-throughs, and give us opportunities in areas where we need to move the ILA technology forward. We've got to get more of those samples. We've been talking that, Mark's been preaching that, and we've got a nice inventory sitting there right now, but we do need more, and we'll be cutting out a number of samples with these long seam defects. Combine the two needs to do the pull-throughs. And then one of the big kickers we've got is with those anomalies that we'll identify, Sean Riccadelia help us with those. I think, and John's probably, O'Brien's thinking along the same lines, he's talked to us. We're probably going to have to start proof testing. If we get out of those 5 folks I showed you that we use, because I can't always expect them to be in the ditch at a moment's notice, we've got to have some op-qual, some kind of proof testing for the NDT that's going to be ongoing in the ditch because of some of the issues that we heard, even with phased array that Harvey brought up. And then the other kicker is we'd really like to work with John, and the group to continue to coordinate and cooperate as we move along into this phase 2 part of the study for why we're up here talking. And that's, I think, yes, that's the end of my presentation. Thank you for listening out there on the webcast. I did get a lot of text messages saying they liked my coat, so I appreciate that.
Okay, thank you very much. We have 2 web questions here. One is for the group, and then one is for Enterprise here. The first question for the group is, besides knowing toughness in the area of the seam weld, how do we measure tensile properties in the area of the flaw? I don't know who wants to take that. Go ahead, John.
Yeah, we'll give that one to John.
I don't know, does this one work? I guess it's on, okay. Well, it is critical to know that, because if you don't have the right tensile strength, use too low a value, you will underestimate or you overestimate the time after a hydrostatic test at which you need to test again. The problem is that's hard to do. The standard tensile test is one way to go, where it's an API test across the weld, and it measures only ultimate strength, really. It can measure the yield strength, but the problem is you're averaging the yield strength of the weld area and the body to pipe. And the tensile test is primarily a test of the weld quality. And if you exceed the specified ultimate strength before the weld breaks, it passes. That's kind of a pass-fail test. Other than that, you can try doing miniature specimens or something like that, but I still think it has to be done perpendicular to the weld to get a meaningful value. But there isn't a whole lot of other options that I know of.
Yeah, and I'd agree with John. We did a little bit of testing, to see how much we'd work hard and, as we flatten those specimens at perpendicular, so there wasn't that much spread. I was surprised, but I wanted to show PHMSA I wasn't work hardening the samples and then pulling a tinsel.
I'm going to respond to the question that came from the webcast. Okay. And the question was, has Enterprise had any hydro failures after inline inspection on that same segment? On that specific segment, we have not run an inline inspection, so there was nothing to, well, we've run inline inspections, but we did not run any CD crack tools on that section.
And do we have any other questions? We have a mic here in the center, and I think there's another mic that'll be floating around. Do you have any other questions for the last panel here for the day? We have one right here.
Gary Wokowski, Engineer Mechanics. I thought I'd make one comment about the fatigue calculations that you did. We do a lot of fatigue crack growth testing on cracks in pipes and specimens and stuff. And I just texted one of my guys and I says, well, for the last surface crack pipe test that you did, how many cycles did it take to initiate the crack versus grow the crack to failure? It took about 1 million cycles to grow the crack to failure, but it was 500 to 800,000 cycles just to get the crack started. So that's probably a bigger factor than your crack growth law that you're using.
Any other questions? Well, thank you very much.
While the panelists are shifting down, I'll just take a, yeah, you're welcome to get out of my way. It's fine. Just to wrap up briefly, you know, we started the day describing that we wanted to share a lot of knowledge that's been done or that's been gained over the last several years on the topic of crack management in pipelines. And I must say, I think we accomplished our mission of putting a lot of information out there. I think we could have gone at least 2 days on this workshop. And for those of you who may have wanted to be a presenter here, I apologize, we just couldn't fit everyone in, but I know there's a lot of good information as evidenced by, the presentations and the people we've had in the room so far, or in the room today. What do we need to do? Bring up those slides. Shut that. Oh, thanks. Yeah. Just. I've got my taskmaster, Bob, who's really keeping me on track here. Thanks a lot, Bob. But anyway, I think, a couple of common themes I think that were kind of resonated throughout the day, and just to greatly simplify it, certainly material properties are extremely important. Particular toughness, I think we heard that talked about quite a bit, about being important to know that and using the right models and using them correctly. Certainly knowing the physical features are important and how you derive those either by inline inspection, the certain tool that you use, or in the ditch method, in the ditch measurements. Knowing the morphology of the features certainly are important, as well as validating what you do know, validating the inline inspection results with actual direct measurement in the field and using of unity plots. People are important. Heard mention of the Mensa pig that we're ultimately trying to develop here. But certainly if we give people the right tools, and that's important, we do need to have the right decision-making that goes into it and the right skill sets that go into the results that come out of the tools. And one thing we kind of sensed, perhaps, is there a shortage of qualified people? I know that's a challenge we have I think throughout the industry, is just making sure we have and bring the technical skills along to keep things moving. Of course, certainly using the right assessment methods. I think Steve did a good job of introducing you to spike testing, and I look forward to some discussion that'll come out of that. I think you can detect that that will be talked about in probably some future rulemaking that come out. I do look forward to the dialogue that we have around that, because we do want to get it right related to what would be a bona fide spike test, for instance, and where that would be applied in your assessment or program. Obviously, there's a lot of work yet to be done. We certainly heard that. There's some research we'd like to see, and that's why we have an opportunity tomorrow for helping us guide where the research goes as far as the research that we fund at PHMSA. So we will have that 2-day session starting tomorrow. That won't be webcast. For those of you on the webcast, appreciate your attendance, but those 2 days won't be webcast. And by the way, over the course of the afternoon, we maintained about 440 to 480 on the webcast. So thanks a lot for your engagement in the workshop here today. And with that, let me just go through a few last minute things, what to expect. I think I've covered that. We will post files on that website link that that's listed up there on the slide right now. For those of you here, please hang on to your name tags. I mentioned that earlier, as we will use the same ones. We are trying to conserve your tax dollars, your user fees, and saving money here, so please hang on to those. Thanks again. I want to say a special thanks to the PHMSA crowd who put this on. Bob Smith, certainly for his logistics work. Kelly Johnson, who is at the front desk, who works with us in our Washington office, as well as Joshua Johnson, Jim Merritt, Steve Nanny, and then John Wolfgram, who's from Minnesota. We value the partnership we have with the states. They are instrumental in these programs that we put on as well, so we certainly appreciate John's help with moderating that last panel. And with that, I wish you safe travels back to wherever you may go, or I look forward to seeing you tomorrow morning at 8 o'clock sharp. Right? Thank you very much.